Everything is ready? Can we start? Dear colleagues, welcome to the third day of the Russian International Conference on Cryo-electron microscopy. And today's morning session is dedicated to the structure of viruses and chaperonins. And the first talk is by Pavel Kanya, the protein stability characterization workshop by Nanotemper. Pavel is from Nanotemper, apparently. Please, Pavel, you have 1 hour.
Thank you very much. Thank you for a nice introduction. Today, together with my colleague, Dr. Semir Ridi from Nanotemper, we will make some kind of workshop focused on our solution for protein characterization. As you can see, I will start from some kind of a presentation, and then I will invite you to watch a recorded demo session of our newest and most comprehensive solution for protein characterization. So as you can see, the title of my presentation today is a new gold standard for challenging stability characterizations and brings DLS to your protein workflow. And at least part, I will focus on our newest implementation in this topic. So the DLS optic will be mentioned here also. So before I will go to some kind of details, technical details, and before I will start to talk about our technology, I would like just to emphasize a few things about general stability of protein that you probably may be aware of. Just give me a second, I think I have some technical issue. Okay, so as I mentioned, stability, protein stability will be the main topic of our today's presentation. And as I already said, this is probably you are aware of the fact that this is a rather complex issue, meaning that when we are talking about the stability of your protein sample, it combines different parameters which all together will bring you the data that you call stability. And our latest effort, our big effort, is always put it to ensure our users, people working with proteins, to ensure that we will give them the highest quality. And here on this slide, you can see that we have few mentioned parameters which only all together can bring you highest quality data. So you can mention here the specificity, limit of detection, resolution, or sensitivity and precision or accuracy. Only altogether will give you what we call a very comprehensive approach toward stability characterization. And as you can see, as you will see on our examples, we are always trying to establish the highest possible quality, which is visible while you are performing your measurements on our Prometheus systems. First, of course, I should also say what kind of proteins we can analyze on Prometheus. And it would be simple to say that you can analyze all types of your proteins. So just we mentioned here a few types, so we can work with virus-like particles. Of course, one of the mostly often targets are monoclonal antibodies in the biopharma industry, or different combinations like ADCs. In academic markets, our users are commonly working with different recombinant proteins, native proteins, or also enzymes and different types of recombinant enzymes too. And what is very important to emphasize here, our technologies are allowing researchers to work also with challenging targets, like, for example, membrane proteins, GPCRs, and many others. Of course, this is just some kind of examples I mentioned here, but almost any type of protein can be analyzed on our Prometheus devices. Why assessing stability of protein is important? Because honestly saying, stability, characterization of protein stability will be your target whenever you are performing different types of applications with your proteins. We can divide these types of experiments into a few groups, like for example, whenever you are performing different buffer screenings or different conditions, whenever you would like to test how different single point mutations are affecting stability. So this will be in this part of screening and comparing. But of course, we can mention here also totally different biophysical characterizations of your proteins. So if you are also structural biologist, also different types of comparison will be going towards comparison of protein stability. And of course, also quality of your protein is also related to protein stability. Whenever you would like to, for example, check how different conditions of long-term storage will affect your sample, you will need to take a look on how the stability of your protein looks like. And this will, of course, affect the functionality when you would like to go with your protein to the next part within your workflow. So there is a lot of different application of different experiments, and in each of them, you will need to have a look on how the stability of your protein looks like. There are a few very generic common advantages of all our Prometheus platforms. So I decided to also put it here before I will show you how we are working with these systems. So for example, something related to my first slide is that we are always making a precise measurements as we are trying to ensure the highest quality. But what's one of the most forwards for our users advantages are also is, for example, label-free detection, because in any type of our measurements available on these platforms, we are not forced to use any external labels. In any type of analysis, you will also have a chance to save your sample. That's due to the fact that we are working in a capillary format. And in a capillary format, we will be using only 10 microliters of your analyte. That's quite cool advantages of our systems. As I said, one of the favorable from our users. And all of these platforms has been also constructed in the way to give you a chance to work with adjustable throughput. You can measure up to 48 conditions in one round, and I think it's a great feature regarding how many time you can save by using nanotemperature solutions for protein characterization. Okay, that was just some kind of a very generic introduction to my presentation. Now, in a few words, I think it's very important to show you how we are measuring, how we are working with the stability. So simply saying, all that we are measuring on Prometheus will typically happen during the temperature unfolding ramp. So we are working in the temperature. You can adjust this temperature ramp up to your choice. So it can be adjusted between 15 and in a typical melting experiment, it can be adjusted between 15 and 95 degrees. And during this unfolding, we will be able to watch different behavior of your protein. These behaviors will be reflected as a colloidal stability also. So beside the thermal stability, which was the first target of developing these machines, you can also detect the formation of aggregates. So we'll be able to detect, for example, amorphous aggregation. And now also with addition of our innovative DLS optics, during this part, you will be also able to detect how the hydrodynamic radius of analyzed protein is changing. So you also will be able to detect ongoing oligomerization moment when it starts, when the particles of your proteins are starting to change their size. This is very unique feature of our solutions, probably the only one on the market that will give you all of this together in a one run. Of course, it is important to at least have some idea how does it look like from the technical concept. So here I prepared a short, simplified schema of how Prometheus Panta systems are working like. So we can see the main point of this construction is of course the tray on which we are putting our samples. The tray is lying on the source of the changing temperature, so on the thermal element. This is of course very important. And above the tray, as you can see here, there are two different, or rather three different optic models. Two of them are taken together. So I can mention here we have a fluorescence and back reflection detectors. So the fluorescence detector is measuring 330 and 350 nanometers, and a back reflection detector is used for detection of amorphous aggregates. And those two were implemented in our systems previously, and now with the launch of our newest solution, Prometheus Panta, we add also the second tube here, which is consisting DLS laser and DLS detector. All of these optical parts are during our measurements working together and moving above our samples and performing the readout. What is very important to mention at this moment, you can see that there is no physical contact between our optics, our device with your sample. Everything is measured in the capillaries. It means for a user, it means that there is no any necessity to perform tedious cleaning or calibration after the run. All you need to do is just to discard capillaries and load a new one if you are, for example, working with a high throughput of your samples. And of course, I think it's good to tell you a few words about how we are assessing different parameters. As Prometheus Panta is a combination of three different optical models. I will start from a description a little bit, the first one, which was originally implemented on this platform. It was nano DSF technology, so the one that I mentioned that is measuring the fluorescence. So on Prometheus, for the assessment of thermal stability, we are measuring only intrinsic fluorescence of tryptophan and tyrosine residues. Therefore, what we are getting as a result of such measurements is a typical binding curve, typical melting curve, which you can see on my slide here. This shape is delivered here from the calculation of first derivative, which will be reflecting the melting temperature, which is a target of this characterization. The typical shape of melting curve is, as it is shown also on the schematic graph, here is coming from the typical behavior of tryptophan residues, which normally in unfolded states are hidden into hydrophobic inside of the structure of your protein. And during the unfolding ramp, what we are observing is the movement of these residues from the inside toward outer area of protein conformation. So this is how we are targeting and how we are targeting thermal stability and melting temperature. The second included originally optic model was back reflection technology, and this one is right now. This one is used for characterization of amorphous aggregation. So for this purpose, what we are doing is to use the incident UV beam that is put into a capillary, and then after being reflected by the mirror, which is lying beyond the capillaries, we are measuring the attenuation of the light. So what our detectors are measuring is the amount of reduced light coming back to it. Due to this construction, we are able to detect the onset of aggregation, but it is very important to mention here that we are using back reflection now to characterize rather amorphous aggregation. So with this module, we are watching aggregates of a size above 25 nanometers. This is the limit of detection characteristic for a back reflection, meaning that everything that which will be smaller than 25 nanometer will remain invisible. And that's why, that was one of the reasons why we also decided to implement DLS module, which is quite innovative in our case. For DLS optics for particle sizing measurements, we decided to implement blue LED laser, which is a source of light in this module. For particle sizing measurement, we are measuring a backscattered light. This will warrant us the highest sensitivity to detect smaller particles. And as you can see on this short graphs, as a raw data, our detectors are recovering this intensity fluctuations. This intensity fluctuations signal are coming from Brownian motion, which are quite natural for all particles. And by using our autocorrelation function, by establishing this autocorrelation function, we are able to get the signal, which will be then used for characterization of diffusion coefficient. And from diffusion coefficient, our software is calculating the hydrodynamic radius of your analyzed samples. It is important that on Prometheus Panta we can use two different models of fitting. So one will give us a cumulant hydrodynamic radius and will show us the situation in the whole thermal ramp during the measurement. And the second fitting model will also give us the possibility to see the size distribution, so we can take a look on different populations present in your analyzed samples too. So as you can see, there are many options, and with applications, I will try to quickly give you some idea what can be analyzed on Prometheus in general. Because definitely I would like to start also from showing you some classical, maybe classical is a good word, classical applications coming from nano DSF. So this is a very classic approach to towards protein stability, showing the combination of only two of our modules. So here on the left, you can see the results coming from nano DSF. On the right side, you can see the results coming from back reflection. So amorphous aggregation in this case has been assessed. And as you can see, even on the first glance, it is very important to compare the data from different detectors, from different optic models, as the results may be a little bit surprising, like it is in this case. So, for example, while looking on stability, on thermal stability, when we tested 6 different pH conditions on a monoclonal antibody, and by looking on this data, you can make a conclusion that, for example, the highest stability with a pH 6.5 will be the best one for this screening approach. But in the same time, while looking on the amorphous aggregation, the same condition used for this monoclonal antibody will give you the fastest ongoing aggregation detected by back reflection model. This is very important, and this is just one of the very classic proof that only comprehensive characterization will deliver you the possibility to select the best conditions. Of course, all of this is tested very quickly in a single run. Here there are only 6 different conditions analyzed, but as I mentioned, you can increase the amount of tested samples in one run up to 48 even. And so this was very also one of older example of combination of these two models. So I would like also to switch a little bit to a totally different field of our application possibilities. Protein stability plays also a very important role while we are performing different kinds of combination of conjugation of your proteins. For example, with different nanoparticles used as drug delivery systems. This is, as I said, different example. So here it was magnetic nanoparticles used to conjugate with transferrin, which was a protein. And as you can see, to be absolutely sure that such a conjugation will not affect the functionality of your target protein, it is very important to test it on to assess the thermal stability. And as you can see on the results on the left side, there is totally differently looking like thermal profiles from naked transferrin, which is marked with blue peaks, and the purple one, which is transferrin after conjugation to this nanoparticle. Of course, it is very important to always have some kind of control. In this case, it was free nanoparticle. Just one more word to make it clear. On the higher part of this graph, you can see this typical melting curves of your proteins, and in the lower part, you can what you can see is the reflection of first derivative. So that's why you can take a look on the peaks, which are characteristic for the melting temperature on the melting curve graph. So anytime you have a possibility to take a look on both of these possible of these graphs. So that's the different approach. Of course, what also will be affecting thermal stability will be different post-translational modifications. So here I would like also to show you that, for example, when we're talking about post-translational modifications, glycosylation and deglycosylation may be one that can be a good example to show how this will affect the melting temperature and aggregation. So we made some kind of a collaboration with a company called Genovis, which is a producer of enzymatic tools to perform deglycosylation. And by using of this enzymatic kits, we perform the comparison of Prometheus to see how these modifications will affect the changes visible in thermal and colloidal stability. And here you can see the results. So we have purple curves for a naked, not modified antibody, and then you can see how this stability was changing when we are performing N-glycosylation or O-glycosylation, or finally total deglycosylation, which was marked by green color. And in this green case, you can see also how the colloidal stability was affected in this case, which was causing to the total aggregation of, which was leading to total aggregation of the protein. Of course, normally when we are talking about analyzing the thermal stability of proteins, what you are thinking is that you have to work with purified protein, but it's not necessarily true. And I just want to quickly show you that we have also examples that were performed on crude lysates, like in this case. So in this case, the researchers performed a high throughput screening on a library of enzymatic bacterial enzymes. So in this case, with overexpression of targeted protein, like 30%, they were also able to get the TM values. And it was quite nice that they were able to perform this type of study in only 2 working days, and almost 600 of different samples were processed. So the message for you from this example is that we can also perform this thermal stability characterization in crude license. Okay, so that's enough about the typical Prometheus applications. Now I would like to show you how these possibilities of our systems looks like after implementation of DLS. So I would like to show you an example of combination of how different can be the behavior of your protein. In this case, it's again a monoclonal antibody in different conditions. So this is an overall view of three different, coming from three different modules that we have abroad on Prometheus. On the upper part, you can see the thermal stability. In the middle, you can see the amorphous aggregation, and the lower part is coming from the DLS. And that's the one showing how the size of the cumulant radius is changing during the unfolding in totally different conditions. If you would like to take a look a little bit deeper, I will go step by step with this example. So first one presented here is the monoclonal antibody in sodium acetate with some kind of addition of salt. And whilst watching on the stability, on thermal stability results, you can see there are free melting transitions characteristic for this antibody from different domains. While looking on the backscattering, we can say that there is some amorphous aggregation starting preceding the third melting transition. But while looking on the DLS, we can finally detect something that was invisible before, and this is the change of the size that's and formation of small oligomers starting rather in a parallel with the second melting transition. So here we are adding something that was invisible without using the DLS, and this is the fact that oligomers, the formation of small oligomers starts even earlier. In the second example, the situation is a little bit simpler, so there is no amorphous aggregation detected at all. So we have a flat line, while looking in the middle graph. There are only two melting transitions in this buffer conditions for the analyzed monoclonal antibody. And important thing that still we are able, by using DLS, to detect something that is happening at temperature 50 and then 68 degrees, because we can detect the growth of monomers. By looking at the scale of cumulant radius, we cannot claim that there is some growth of oligomers, of some kind of oligomerization, but still we can detect the changing size of monomers in the solution, and it was again undetectable before. And then the third one is just to show you that in three different buffer conditions we can get totally different data. This one is showing that both of these models, so back reflection and also DLS, can deliver data which are corresponding. So here we have amorphous aggregates and very small difference between the results coming from the DLS. So DLS detects the growth of oligomers at 79 degrees, and back reflection is talking to us about 80 degrees. So this is a nice parallel. So that was the results coming from the cumulant fit. So as I said, this is a very unique feature of Prometheus, that in a one temperature ramp we can deliver you all of this data. But I mentioned also that we can use our different fitting model to assess and to characterize the homogeneity of your analyzed sample. And from this type of analysis, you will get data looking like this. So, it will be rather talking about the different peaks for different populations of molecules present in your samples. And the most important factors received by performing this measurement will be PDI. This is a polydispersity index parameter, which will tell you about the homogeneity of your sample. So the lower PDI, the more homogenic your sample is. And it was the comparison made between the bovine gamma globuli and standardized monoclonal antibodies. So there is no big surprise that in case of monoclonal antibody, we'll have a nicer peak of this analyte, reflecting the higher homogeneity. And in case of bovine gamma globulin, we have a broader peak reflecting the heterogeneity of this sample. And we can detect few populations, so this is extremely helpful while checking, for example, purifiness of your protein. Besides heterogeneity and homogeneity assessment, DLS included in Prometheus Panta can be also used for very helpful characterization of self-interaction of your protein. To perform this, we are using we are measuring the diffusion coefficients of your samples in different concentrations. And by using this, by performing this determination, we can get the different values of self-interaction KDs. And here are two opposite examples showing that we can get negative KD values, which will be a reflection of attractive tendency of self-interaction of your protein, and a positive, which will reflect the repulsive tendency. In a kind of attractive interaction, it means that probably this therapeutic candidate can cause some kind of problems, while, for example, handling with viscosity, with a higher viscosity, and for therapeutic usage, it may be very important to use higher injection volume to a patient, and which is something, of course, that we would like to avoid. Positive KD will rather tell us about the protein, which is more prone to overcome complete solvation, which stands in opposite to negative value, which is talking about the self-association tendency. This is made by a calculation, but this is extremely important and we met very enthusiastic welcome of this type of approach from a pharmaceutical industry. So I think this is also something worth to remember and to connect with. To quickly summarize all of this data, which are coming from usage of Prometheus, you can find them here on this slide. So there is a lot of different parameters. As I said a few times, we are talking about a comprehensive characterization. So that's why we are able now to deliver you a lot of different parameters to characterize your protein in general. Just one more thing to mention, that we are also very elastic in the field of format that you have to work. So it is true that we are working with a small sample volume, but regarding your experimental throughput, you can select between working on the capillary chips, which are constructed in the way that are very easily, that can be very easily loaded from the 384 well plate. But if you are working in not so regulated throughput, you can always switch the tray to work with single capillaries and load up to 48 in one. And just to finish, this is the summary of our whole Prometheus systems family. So we have still 4 versions of them. Of course, this is something I will not take your time now. If you would like to get more information about the differences, we can discuss it. You can discuss them with your distributors, and we can, of course, support you with this discussion. And with these words, I would like to thank you for your attention from this part, and of course, please stay with us and watch our online demo, which I think will be even more interesting than just listening to my presentation. Thank you very much.
Thank you, Pavel. And now we switch to video presentation.
Hello, everyone from the Nanotemper headquarters in Munich, Germany. My name is Samir Jaridi. I'm a senior application specialist here at Nanotemper, and I want to demonstrate you today how easy it is to start DLS and nano-DSF experiments with the Prometheus Panta. So for those of you who maybe already know the Prometheus, you can see from the outside, not very much has changed. The display has improved, so you get now much more information about the ongoing experiment. But other than that, from the outside, it looks very much the same. But let's just dive right into starting an experiment. And the first thing that I have to do is load the sample, of course. So for this, I will just open the drawer using the touch display. And now you can see the sample tray comes out. So this is the thermal element where the capillaries will be placed. So what I have to do, first of all, is remove this metal lid that is there to keep the capillaries in place and to press them down to the thermal element to make sure that they are in close contact. And now here you see the thermal element. Maybe you can see that it is a mirror surface, and this is because of the back reflection optic that where the light is going through the capillary is reflected on the mirror surface and is going back to the detector. So this here is the adapter that takes the capillaries. You can place up to 48 capillaries into this capillary adapter. Each of the capillary position is also labeled with a number, so it's very easy to keep track of how many capillaries you have already loaded to the device. So the single capillaries I will use for this short demonstration today. What you can also use is we have another consumable type, and this is if you want to probably measure more samples, you are maybe more in a screening type of applications, and you want to load your sample from a 384 well plate. And for this end, you maybe want to use our capillary chips. So they are the same capillaries, but they are placed already on a chip where 24 capillaries are placed on. So you can measure 24 capillaries at once. In order to do that, you can just remove the capillary adapter, and now you can use the chip. It's very easy to load sample into the capillaries, and the format matches exactly the distance of a 384 well plate. So what you can do in order to load sample is just prepare your sample in a plate, dip the 24 capillaries all at once into the 24 wells of one row of a 384 well plate. The chips will load, or the capillaries will load within 1 or 2 seconds, and then you can place all the 24 capillaries at once into the device, put the lid on top, and then you're ready to go and start the experiment. So for this today, as I said, I just want to measure a few single capillaries. So I just remove the lid, remove the chip. And in order to use the single capillaries, I just add the single capillary adapter again. And now I can use the single capillaries. The single capillaries come in these little vials here. And what I usually do is I just pour a few of the capillaries out and put them into the lid, which makes it a little bit easier to take them from there and load them into the device. So I brought some sample. One of them is a special standard BSA solution that is also used for evaluation of the device. And as I said, it's very easy to load the sample. You just dip the capillary into the tube, and within 1 or 2 seconds, the capillary is loaded by capillary force. And for this measurement, I'm going to do a duplicate. So for this standard BSA sample, I'm expecting to see a very good homogeneity of the sample. And the other sample that I brought is BGG. This is bovine gamma globulin. So this is basically a mixture of different subtypes of antibodies. So here I'm expecting to see less homogeneity in the DLS experiment. Again, I'm going to measure duplicates. So I'm going to load a second capillary from the same tube very quickly. And that's it. So in the end, I just have to place the lid on top to keep the capillaries firmly in place. And that's it. And now I can go on and start with the measurement. So I just have to close the instrument with the touch display. And now I can control the device with the software from the control PC that is delivered with the instrument. So we have 2 types of software for the Prometheus Panta. One is the control software that I will use now to run the experiment. This software is not only used to run the experiment, but it also gives you already the results like TMs and the sizes also that can also be exported as graphs and as tables as well. However, we also have a dedicated analysis software that is much more sophisticated, that allows you to combine different measurements from different days, for example, and generate statistical analysis and also generate nice graphs and tables to export. So I will focus now, of course, on the Panta analysis, Panta control software to run the experiment. So first of all, what I could do is, of course, I could browse recent projects, previous projects, to add more measurements to an existing file. But in this case, I want to start a new file and I want to run a new experiment in a new file. So here it starts with a little explanation what to do. We have already done that. Just if you need, you can get this information. But now the first step would really be to just run the discovery scan. This means that the device will use auto detection to find the right excitation power and then scan the capillaries to detect the capillaries that have been loaded and to already define the best excitation power to be used for a later nano-DSF experiment. So here you can see already the results. We can see that the 4 capillaries have been detected. All the other capillary positions have been detected as being empty. And it's a very nice confirmation to see that the duplicates are very similar. And as you can see, the BSA is a little bit brighter than the BGG. This depends on the concentration, but also on the sample, on the amount of tryptophans. So as you can see, the excitation power that was chosen by the device was 33%. You could run an additional discovery scan, for example, with another excitation power, but this is really not necessary at the moment because it is already fine like this. So you get the the fluorescence, and also down here you get the DLS scattering information and the turbidity information just at the beginning of the current of the capillaries. So now this was the experiment setup. The next step would be to add a measurement, and if I click here on this button, I can then, as a next step, choose what type of experiment I want to run. So basically there are these 2 modes. First, there is a size analysis experiment. This is basically an isothermal DLS only experiment, so there is no unfolding of the protein. And the other option is the thermal unfolding experiment. This is where the sample is heated up and the protein is unfolded. And here we measure the nano-DSF with nano-DSF, the unfolding, and at the same time we measure the turbidity with the back reflection and the sizes continuously with the DLS. But of course, it makes sense to start with the size analysis experiment because here we don't melt the protein, and then after that we would run the thermal unfolding experiment. Here is another option for the self-interaction analysis. This is now in gray because this is an analysis that is only possible once there is measurement ready from the size analysis. So we are not going to use this at the moment. We will start now with the size analysis experiment. So now you can see the 4 samples, the 4 capillaries that were detected. I now have a chance, or at any time later or during the experiment, to give it a name for the sample. Another thing that you can enter here is the solvent, and this is relevant because the viscosity of the sample will also define the sizes that are measured. So usually this is not really relevant if you have just a regular buffer with maybe some salt and some different pH. It's not super influential on the viscosity. So this is just a normal saline buffer. However, if you would have a lot of sucrose or glucose or something like that in your buffer, this would change the viscosity. And if you want to have a very accurate measurement of the size, you would want to correct for the viscosity. So this is why you have this drop-down menu of different buffers. If you want to add a buffer that is not present here by default in the drop-down menu, you can also manage your solvents. You can create a new buffer, give it a name, for example, new buffer. You can add a number for the viscosity if you know it from literature, literature, or if you have maybe measured it in a viscosimeter, you can add that value here. Or if you don't know the viscosity, there is also an option to calculate the viscosity with the viscosity calculator. So here there is a list of very typical chemicals that are used in buffers, and you can add, for example, let's see if I can find sodium chloride and maybe some sugar like glucose, and then you can add the appropriate concentration. Let's say it's 150 millimolar of salt. And for the sugar, let's say it's 1 molar. Of course, this would be a very high viscosity. If I would say it's 1 millimolar, you can see the viscosity is more like a regular buffer. So if I apply that, I have this new buffer, and I could add this now to my solvent list. At the moment, I don't need that. I just wanted to show you how you can manage different solvents in case you have a buffer with a very different viscosity. Okay, so regarding the settings for the DLS experiments, it's very simple. Basically, all you have to enter is the temperature at what you want to measure. So we will do it at 25 degrees. And then there are basically just two options. One is if the high sensitivity is turned off. This means it will be a very fast measurement. It will take only 10 seconds. But in this case, I would like to go for the high sensitivity. This means in the low sensitivity, it's only 5 times that each capillary is measured. And each capillary will be measured for 500 milliseconds. If I go for the high sensitivity, each capillary will be measured 10 times for 5 seconds in order to measure the fluctuation of the scattering signal. So this is all really that I have to set, and then I can already start the measurement. I can now hear the measurement starting, and you can see here now on the left-hand side, this is already the size distribution plot as a violin plot for each of the capillaries. So the first 2 capillaries are the BSA solution. The third and the fourth capillary are the mix of antibodies, and you can already see that the sizes look very different. In the middle, this dot is the cumulant radius, so that's the average radius of the sample. And then this bubble around it is basically the size distribution plot. And here you can see if there are different sizes present. So in some cases, there are tiny amounts of larger aggregates that are visible here. And this is the size distribution. Now on the right-hand side, you get a table with some details. So there's the sample name, the number of acquisitions that is now going on. So we have now 3 acquisitions, and we'll come to the first acquisition now. And then you see also the results. So there is a cumulant radius, which is the average radius. So for each of the sample, for each of the capillaries, and the standard deviation coming from the different acquisitions that we have at the moment. Then there is also the cumulant polydispersity index. And this is a number for the homogeneity of the sample. So as I would have expected, the BSA, which is a pure sample, has a lower polydispersity index than the mixture of antibodies, which is less homogeneous. So this polydispersity index is a very nice parameter to assess the quality of your sample, and you can really optimize it, for example, in a buffer screen to really find the best buffer for a really compact and monomeric protein and the absence of larger particles or aggregates. Other values here are the scattering intensity, and then signal to noise is a very nice parameter to just see and learn about the quality of the measurement. This between 1 and 2000 is a very good signal to noise, but it can be of course lower, and that depends if you go, for example, with very low concentrations of protein. Another view that you can look at is the autocorrelation function details, ACF details. So here you can really look at the raw data for each of the different acquisitions of all the capillaries. So we are now looking at capillary number 1. And here we can look at the different acquisitions. So this is acquisition number 1. Here you can see acquisition number 2. And what you see here in detail is the autocorrelation function coming from the analysis of the noise, of the fluctuations of the scattering signal. And if you zoom in, you can see that there are actually two fits. One is the cumulant fit, one is the size distribution fit. And these fits are used to calculate the cumulant radius that is shown here as a dashed line, and then the size distribution that is shown here as this curve. And this plot is basically the same one that is then also plotted here on the left-hand side, where the cumulant radius is here the dot in the middle, and the size distribution is this violin plot here around the dot in the middle. So here on this side, you see for each of the capillaries the different acquisitions on top of each other. That comes from these raw data here. And then you also have this additional view where you can look at the average size distribution. Here you have then the average for each of the capillaries. So for each capillary, you have one curve. And here you can see very, very nicely the difference between the sample again, where the BSA, which is a pure sample, has a very nice and narrow peak, and it is also clearly smaller than the other sample, which is larger in average, and also the peak is broader, indicating less homogeneity. And this, as I said, is also represented in this value, this very helpful value, the polydispersity index. So now you can see that the measurement is already complete, and it tells you here that it's completed. And also you have now this button active where you can go to the next type of experiment. So the next experiment that I would do, of course, is the thermal unfolding. And here, again, of course, the sample is still the same, so the information is still the same for the sample. And now the settings that I can choose from is actually, again, the start temperature, and I would use the 25 degrees where we are already at the moment, and then the end temperature of the heating, and this is usually 95 degrees. Another important parameter is the temperature slope. So this is the heating rate, how fast you will heat up the sample. People usually choose 1 degree per minute, but you can also go much slower. In the end, you get here a duration for the whole experiment. So if I go with 1 degree per minute from 25 to 95 degrees, this would take 1 hour and 10 minutes. Of course, I don't want to do this now. So instead, I can change that and go to 7 degrees per minute, which is the maximum speed. And of course, this will be a much faster experiment. It will now only take 10 minutes. You also have the option to turn off or on the dynamic light scattering. This means if I turn it off, it will be more like a regular Prometheus unfolding experiment. So this will only record the nano DSF and turbidity without any DLS measurement at the same time. This means that the data point density will be much higher because there is no need to record the noise of the scattering. Instead, the scanning is much faster. But of course, for this experiment, of course, I want to, at the same time, measure the particle size during the unfolding. So I want to use DLS. Still, the data point density is fine. There's also an internal check here, and this would give you the feedback if the data point density would be too low. But here the software tells me that the data density is sufficient, so I can go on and start the thermal unfolding experiment. So you can now see the first data points already appearing, and in this default view, the overview, you can see all of the 3 parameters, main parameters that we measure. So first of all, there's the fluorescence ratio that will in the end show you the unfolding of the protein. Here in the middle, you see the turbidity that can show strong aggregation and changes in the turbidity of the sample. And down below, you see the cumulant radius that actually measures the actual sizes of the particles that are present in the sample and how they change during the unfolding experiment. So this, of course, will now take a little bit. In the meantime, I can already tell you that there is different options to view the data. So you can look at the data points, you can generate a smooth curve, or you can look at all of this together. And there are different ways to look at the data. So this is the overview that gives you the main parameters. There is also a focus on nano-DSF, where you get the ratio, but also the single wavelength. And then there is also a view that focuses on the dynamic light scattering, where you also get the details of the raw data, but also you get the scattering intensity, the cumulant radius, and then a very nice plot of the size distribution. So basically this is this plot here, but it's plotted over the temperature. So that's very interesting additional information. So this will take a bit. So I think the best is to just jump a few minutes ahead and see when the experiment is completed. So now the measurement has reached the end temperature of 95 degrees. The measurement is completed. And now you can see that there have also been automatically by the software some markers added. So this is the midpoint of the transition for the BSA and also for the antibodies. This is the melting temperature basically. And it's very nice to see how well these two replicates of each of the sample overlap. So maybe I will also use the smooth curve on top. And you can see that it basically looks like it's just one measurement, but actually these are the two replicates. And this is something that we are really used to from nano-DSF, but it's also very nice to see the same reproducibility also from the DLS size measurement. So as you can remember, the BGG, the antibodies, were clearly larger than the BSA, and you can see that here in the beginning. And then you can see how the BSA just slightly and continuously increases in size. So this is more pointing towards oligomerization, while the antibody clearly largely increases in the size until there are large aggregates that are also really picked up by the aggregation detection by the turbidity. So here really the turbidity changes, and this is measured by the back reflection optic. So this is the overview. You can also look at the nano-DSF in more detail. You can look at the light scattering in more detail, where you get this really nice additional information about the different particle sizes that are represented as a size distribution plot over the temperature. And you can also create custom tabs where you can decide what exactly you want to look at. For example, the first derivative and maybe the cumulant radius and also the size distribution. For example, you can give it a name. I'll just call it 1. And then you can create your custom view. Here you can export all of these views. And so there is a lot that you get already in this software. Of course, in the data table, you get the numbers that have been determined for the onsets of unfolding, but also for the inflection point, which are the melting temperatures. And so this is already giving you a lot of results. But of course, we also have this dedicated, more sophisticated analysis software to really generate graphs and generate statistics about your data. One last point I would like to point out is that you can always relate to us when there are questions, but there is a very nice document for looking if you have questions. So whenever you see this little icon here, this stands for our Nanopedia, and then you can get to a collection of very helpful information, for example, where you can read about DLS, and other more specific questions regarding the software or data interpretation. So there is a lot to learn already directly coming with the software. Okay, with this, I'm at the end of this short demonstration of our Prometheus Panta instrument. Thank you very much for your attention, and I'm very happy to take questions.
So we don't have much time for questions, provided there is very nice manual. You can consult it anyway. But please, just one question here from the auditorium.
Yes, thank you for a very inspiring talk. I have a small technical question. What are the capillaries are made of? Are they coated from within with something? I mean, how do we count in the opportunity for interaction of the molecules studied with the material of the capillaries? Thank you.
Pavel, can you hear us?
Yes, I can
Okay.
hear you. Just again had some technical issue with connecting. So, yes, we have for Prometheus, for general Prometheus family systems, we have two types of capillaries, and both of them are made of a glass, of a quartz glass. So this is something quite special. We are not we're normally not talking about very technical details about the material what our capillaries made of. Just what I can share with you is the fact that one special type of capillaries is dedicated for assessing stability with very low concentration of your protein. So this is a high sensitivity capillaries. I don't know if Samir would like to add something to my answer regarding this. This is something which is already also patented from our side. Typically these capillaries are made of a very high quality quartz, and that's what I can tell you. Samir, would you like to add something?
No, thank you.
Okay, thank you. Thank you very much, Pavel. And we need to switch to the next talk by Matthias Wolf from Okinawa Institute of Science and Technology, Structural Dynamics of the Curved Flagellar Bacterial Flagellar Hook. Matthias, can you hear us? So you have 30 minutes. Please, welcome. Bacterial flagellar hook. Please, Matthias. Oh, now.
Okay, am I live or do you guys hear me?
Yep. Okay, go ahead.
So I can start my talk?
Yeah, sure. You can start.
Okay, great. Yeah, so thank you very much for inviting me and giving me this great opportunity to talk on this conference. I have been at the last conference in person in Moscow, but unfortunately this time that did not work out because of COVID. As you can see from this intro slide, I'm lucky to work on this beautiful island, Okinawa in Japan. This is a picture of OIST, the Okinawa Institute of Science and Technology. In the background is the Pacific Ocean. And you can see 3 of the 5 lab buildings that are now finished, or the last one is still under construction. So I will talk about a paper that we published last year. The co-first authors, Dr. Shibata and Dr. Matsunami. And this was in collaboration with Professor Shinichi Aisawa at Hiroshima University. Brief background, bacteria swim with flagella, and the species that we studied was Salmonella enterica. So Salmonella is a very important bacterial pathogen that infects the intestine mostly, and it causes diarrhea. And this diarrhea can be deadly, in particular in children, and it's widespread in the developing world. It, is part of water safety and hygiene, and it causes a huge economic burden every year in the billions of dollars in the United States alone, and it kills 500,000 of children under 5 every year, according to the Gates Foundation. Now, bacteria swim with flagella, and the flagella and the bacterial motion are important for the pathogenicity and to form biofilms. So most of the bacteria have this flagella, and the flagella are connected to the rotary motor by a structure called the hook. So here on the left, you see, an electron micrograph negatively stained of a bacterial cell with multiple flagella. Some bacteria have only one flagellum, some two, some multiple ones. And this particular one has it attached on the sides and at the ends. And these flagella, they sort of bundle up to work together without tangling, which is amazing by itself. And they point in the same direction. While their motors spin, in the cell wall. And here on the right side, you see sort of a close-up of this structure, the bacterial flagella motor. This is called the basal body. It's connected via the hook to the flagellum. And the flagellum is a rigid structure that acts sort of like a propeller, like a long, elongated corkscrew. And the hook is a flexible joint. It's a little bit like what you can imagine, like in a car. The CV joints in a car, what in German is called the Kardan joint. It transmits the rotary motion around a bend around the corner. And this blue part here is the hook. And so the motor rotates up to 300 hertz in these bacteria. That's 18,000 RPM. And it transmits the torque to the filament that acts like a propeller. So when we set out to do this, we knew that, first of all, the structure is a helix. There were structures previously, by Professor Number's group, of the straight hook. And the straight hook is a cylinder, essentially a helix of protein subunits. But in nature, sort of under native conditions, this helix is coiled again. It makes a super helix, a super coil. And so we knew that when you adjusted the pH, you could adjust the helical pitch, the supercoiled pitch. And we adjusted it just so that it would be flat, essentially no pitch at all, no supercoiled pitch at all. So not straight, but strongly curved, but essentially we wanted to make rings, just like the one here on the top. And under these conditions, when we put it on with negative stain on the grid, we could see that these structures, they were lying flat. And the idea was that we're going to determine these structures from many of these little rings by single particle analysis. But then when we put it into ice, we found these beautiful corkscrews, like the supercoiled helical polyhooks. So I didn't say this, but these are polyhooks. There's a strain that has a length regulation gene knocked out, so they make much longer hooks than the one that is only about 90 degrees. So these hooks, they're much longer, but the structure is exactly the same, they grow longer. So in ice, you could see these sort of beautiful structures, and they're three-dimensional, because when you look at the class averages here, after cutting them out in segments and then doing rotational and translational alignment, you can get to class averages, and they contain some cross sections. So obviously, these dark parts here, and on the right, the contrast is inverted because it's deconvoluted with the contrast transfer function. And then here you see some of these cross sections. Here's a particular nice one, and you can even see the lumen inside, which is the channel that is used by the bacterium to export the unfolded protein to the tip of the growing flagellum, because these flagella, they grow from the tip, and the inner channel transports these unfolded proteins. So in the class averages already, one could see, the signature of secondary structural elements. These little lines there, they're sausages. They're alpha helices, they're not sausages, but alpha helices. And another feature you can see is that at the outermost curvature, sort of the strongest curvature, the subunits, they come apart, just like you would think of an elastic like a spring, when you bend it. On the outside, they're farther apart, and at the inside, they're closer together. And then here's another example. And this was already evident from the 2D class averages. And then after we reconstructed this in 3D, here what you see, so we could refine this, reconstruct it to high resolution, essentially sub 3 angstrom resolution. And here you see 3 class averages. There's 3, actually, I think we only had 3 class averages. And they are played back one after the other. And on the top, you see a cross-section, and on the bottom, that's a projection of the entire volume. So you can appreciate from this movie that these 3 class averages, when played back one after the other, they are very similar. So in other words, the structure as it was rigid, and it was a unique structure, even after reconstructing this data set from projections. And another thing I should say is that because the conventional methods, they don't allow the application of both the helical symmetry and then the supercoiled symmetry. This structure was entirely reconstructed without any symmetry. So it contained the final symmetry of the object, and it was quite isotropically sampled, but this was reconstructed without any symmetry. And you can see that it nevertheless went to very high resolution. So the cutoff at Nyquist here is not at 0, because this was the limit of our sampling. We should have oversampled this even more. I think the pixel size was 1.4 angstroms. So it essentially hit Nyquist, and it could have gone to even higher resolution. Yeah, this is a rendered surface isosurface view of the reconstructed electron potential map. And you can see that it is very nicely defined. The alpha helices have good side chains. You see in this cross section, you see the channel inside, and then this is a sort of a radial slab through the filament. The hook. And then I want to point out 2 features. I mentioned before that on the outside, subunits must sort of be separated more than on the inside, where they're sort of compressed, because the whole structure is bent. It's not a straight filament, a straight helix. It's a supercoiled helix. And we call this outer line here, where the subunits are spread most, the so-called outermost line, or OML, and on the inside, this is the innermost line. One more feature here to point out: the subunits itself. This structure is made of a single protein, and it is arranged in a helical lattice. In this ellipse, there is indicated more or less, a single subunit, whose polypeptide goes from the center of the channel all the way to the outside through 2 domains, and then it comes back to the innermost domain. And so when we took each of these structures and we extracted them one after the other as you go through the helical staircase, and we built an atomic model into it, and then we could extract each of these models. And then when you superpose the models, in this case on the innermost helix there, on this DC domain, the D0 domain, this part, the green part, and then we superposed them, we found that there's this swaying motion. So we calculated the geometric center of the coordinates in the D0 DC domain, and then in the D1 domain and in the D2 domain. And these are indicated by these spheres. These are sort of the geometrical centers of these atomic coordinates. And then we could measure for each of the 11 subunits around 1 helical turn. We could measure the distance and angle here. And then when you superpose them, you see that as you go around the helix, the subunit sort of sways when it's aligned at the D0 domain. And this is also plotted here, the angle and the distance as it varies when it goes around. And it also, when you look at these aligned structures from the top, like here, it makes a little bit of a sort of a rotational precessing motion, sort of, in a way. And this, why is this? Well, I told you that it's a supercoil. It's not a straight helix. In a straight helix, there would be no variation. But because it's bent, these subunits have to change their conformation as they go around. And then when we aligned it at the the central domain, the D1 domain, we found that, you know, the top and the bottom, they were sort of deviating. And it turned out that, you know, when you analyze this a little bit more carefully, there was a hinge region that essentially allowed a flexible motion. So in other words, the conformational changes that occur as the subunit as you go around the helix, they are essentially rigid body motions of the domains hinged upon these hinge regions. And yeah, we did a sequence search and an alignment, and, you know, and we found that essentially these hinges, they are conserved throughout most of the bacterial kingdom, and as well as in gram-positive and also in gram-negative bacteria. So the ones that are boxed here, these as examples for gram-negative bacteria. They all have these hinge regions that are composed in a very similar fashion. Now, when we analyzed this a bit more comprehensively and compared the subunits as you go up this supercoiled structure, so it takes 11 subunits to go from, I hope you can see my cursor here, from one subunit up to the next. So if you go around and count 11, and then you arrive up here in the pink one, that's a little bit higher, and then the next one and the next one. So it's the subunit number 11, 22, 33, 44, and so on. So when you take these subunits that are, you know, 11 subunits apart, and you superpose them, then they turn out to have the identical conformation. So in this case, we picked the ones on the outermost line, which are the blue ones here that are separated most. And when we superpose them, you can see 6 of them are superposed that are extracted from this reconstruction, and, you know, it turns out they are almost identical, and the innermost line the same. And so you can pick any one of these parallel lines to these highlighted ones, and they will have the same conformation. And so these directions, these lines, they were previously known, they are known as protofilaments. So this goes back to another species of bacteria, you know, where that people thought that it was essentially a physically covalently linked protofilament that would build the entire filament. But in the case of Salmonella, this is not the case. You know, they are not covalently linked. They are individual subunits. They're essentially all the same subunit, but they have different conformations. So we found 11 discrete conformations in this structure. Yeah, well, and then, you know, because we had high enough resolution and we could study the interactions at different between the subunits, we could identify the most important interactions that linked subunits with each other. And these are listed here, and they are sort of, there's interactions between the outside, specific interactions that are mediated by the D2 domain, and then sort of the central cylinder, which is the D1 domain, and then finally the core, which is the D0, mostly alpha helical bundles. And so we thought, well, how does this work? When the bacteria swim, their flagella, they point in one direction. So, you know, if you would rotate like on the left, if you would rotate like this, it wouldn't work. You know, like it has to be pointed in one direction and sort of rotate into and out of itself, just like shown here. So for this rotational mode, as suggested by the structures, as the subunits come apart on one side and then dynamically go together again on the other side, you need 2 hinges. You cannot do this with 1 hinge. And otherwise you would get that rigid type of rotational mode. And so here again, you see the outermost line and the innermost line highlighted. But this structure is obviously, this is not how it's in nature. In nature, you have only about 90-degree turn, so about 200 subunits. And yeah, because we had all these 11, you know, we had the 11 conformations, we could animate this structure in silico, and simulate how the real hook would rotate if we didn't make a movie of this, but we could reconstruct this motion this way. And you can see from the previous one and also here that the distance between these two domains, it varies dynamically as it goes around from the innermost position to the outermost position. And then in this last one, sort of you see a single protofilament, and you see how they're nicely coordinated. Now, when you look at this, they're not coordinated by sort of an axial interaction. There is no interaction besides at the core where these alpha helices are. Now we thought about how does this work, and if the presenter the organizer could maybe briefly switch from my screen to my own view. I want to show you. So we 3D printed these subunits, and we designed little hinges in there. So there's sort of a door type hinge, and then this one has a ball joint hinge, and these heads here, head domains, those are the D2 domains, and then the inside is D0, and they come together nicely. And we also made a little holes in there, sort of that we can string a wire through it. And then this way we printed 200 or 180 of them, and we assembled the entire hook. So this hook is now made of rigid, plastic subunits that are hard, but they're hinged just like this thing, so it feels very organic. And as you can see, it can nicely bend and rotate, and it does exactly what it does essentially in our reconstruction. And it has central channel inside. So you cannot hardly see it, but there's one thing that you may notice is so in one way when you twist it. So it tightens up like a rope, but the other way it becomes sort of loose. And I'm not sure if this is very easily visible here, but when you bend it and twist it, these D2 domains, you can appreciate that they're coupled together sideways, and it's the D2 domain that, by doing this, relays the conformational state of one subunit to their neighbor. We can go back to the presentation now. Thank you. So this motion, is responsible for coupling the subunit conformation to their neighbor. Could we please switch back to the slideshow?
Excuse me, Matthias, you have 3 minutes to go.
Say again, 3 minutes. Okay, all right. I'll wrap up. So some questions are, so I explained how they are coupled, how they are synchronized. Then, what causes a supercoiled state? Well, if you put those in ice, like in water, then they adopt their supercoiled form. So they must have some internal strain. And one example for this sort of so-called zero stiffness structure is this angle pulse lamp that stays in its position, and you can reposition it and it stays there. And so this strain is built in, and we have a pretty good idea why this is. So I will skip over this. Essentially, I maybe should say this. The classical models of allosteric cooperativity, like Monod, Weinmann, and Changeux, and Nemetic, Filmer, and Koshland, they don't apply, because this is not an enzyme. It's a mechanically linked structure that acts as rigid body that's coupled and synchronized, and it has 11 distinct conformations that we could identify. So it has more than the previously thought two states. And yes, I essentially explained the rest of it. So finally, I want to thank again the authors and my contributors and you for listening. So if you have any questions, please ask.
Thank you very much, Matthias. Amazing pictures, and
thank you.
Do we have questions from the offline auditorium? And let me check our chat. There is one question from online chat, please. No, not yet.
I'm sorry, I cannot hear any of the questions.
In meantime, I have one question concerning the hook curvature. Is it constant, or it is adapted to this rotation speed?
That's an interesting question. Actually, I don't know the answer to this. So I know that you're probably talking about this supercoiled pitch, about, how tightly the helix is coiled. That varies with various parameters. One is, the pH, and I believe there may be also an influence by the mechanical force. So if this is the case, then, if this would be the case, then what you asked is probably, what you suggested is probably correct, that if the mechanical force changes, that it could adjust. However, it is known that there are discrete helical pitches. There is only about sort of 11 have been found that that are always unique. So there must be. So there is an internal mechanism that causes this strain, and we think it works like a ratchet. And so when it slips to the next stop, essentially like it goes to the next pitch. And in a way, this probably works a little bit like a variable pitch propeller, where you can, indeed, so it has been shown by people like in Japan in particular, Professor Hotani, that the pitch can be varied dynamically. So maybe this is a way for the bacterium to adjust to different viscosity when it encounters different viscosity, to go to different helical pitch to maintain the same motor torque. But I guess I'm over time now, so I can only offer this explanation for your question right now.
Okay, thank you very much anyway. And here is another question from the chat. Which classification approaches or strategies did you find the most efficient to 3D classify your system?
So I should maybe say two things. So first of all, this didn't use any symmetry. It is in a way a reference biased method, because we started with essentially a cylinder that was bent. And that is a sort of the template that you used for your images to snap into. So it is biased by this template. And as you go to higher resolution, and this sorts it out, we had to sort of restart this procedure several times. But it worked best with program packages like System. And it did not work with Relion. It did work with CryoSpark. So we think that System probably has a little bit more reference bias than Relion's algorithm. And there are probably ways in Relion to tweak this to, introduce more reference bias and make it work there too. But essentially, this method of alignment takes advantage of the bias. Without any bias, it wouldn't work, because then it would be evenly distributed. So you have to have a curved structure, otherwise it doesn't work. You cannot align a helical structure that is straight, a projection from a helical structure against the cylinder. It will never work, because there will always be preferred orientation. But as soon as this is bent, it sort of snap into the mold, and there are characteristic views where it fits. And only then this method works. So it's a niche method. And we are actually working on, symmetrizing this properly, so to apply the full supercoiled symmetry on it. And that should allow also to improve the resolution a little bit. But yeah, so I hope that answers the question. So in terms of classification methods, we use the standard 2D and 3D classification that was available in system.
Okay, thank you very much. And thanks again for your nice, inspiring presentation. And we have to switch to the next talk. Thank you
very much.
Matthias. Thank you. Bye-bye.
Bye.
Now it works. So our next speaker, Min-Yan Su from Shenzhen University of Science and Technology. A structure of C9 or F or 72 complex haploinsufficient in ALS and FTD. Min-Yan, please.
Thank you for the nice introduction just now. And also thank you for having me today and to give me this great opportunity and to share my work. And my name is Min-Yan Su. I'm an assistant professor at the Southern University of Science and Technology from Shenzhen, China. And today I'm going to talk about the structural and biochemical catalyzation of C9orf72 complex, which is haploinsufficient in amyotrophic lateral sclerosis and frontotemporal dementia, also known as ALS and FTD. So ALS and FTD are two different kinds of neurodegeneration and disorders. ALS is caused by the death of the motor neurons that controls the voluntary muscles. So therefore, patients, they cannot speak, swallow, or have any muscle movement. On the other hand, FTD is caused by the degeneration of the frontal or temporal lobes of the brain. Therefore, in the patients, they may have impairment in the cognition or behavior change. However, some ALS patients, they also have FTD symptoms. And therefore now, these two diseases are recognized as spectrum disorders with pure ALS or pure FTD located at the both ends of this spectrum. And this new clinical spectrum is further supported by their shared genetic mutations. And in particular is this C9orf72 gene mutation. So based on the statistics, C9orf72 mutation is presented in around 25 to 37% of familiar cases of ALS and FTD. And it also it contributes around 6 to 7% of the sporadic cases, respectively. Therefore, the mutation in C9orf72 is the most abundant, most common cause among the known gene mutations. So what is this mutation? So in the gene of C9orf72 or say chromosome 9 open reading frame 72, there are this hexanucleotide repeat, 4G2C repeat in the first intron region. So in the healthy individuals, the repeat numbers for this 6-letter string is just around 20 to 30. However, in this ALS FTD patients, this 6-letter string, they can expand hundreds times or even 1,000 times. So now two different mechanisms are therefore proposed to explain how this abnormal extensively expansion can cause this progressive loss of the neurons in these patients. And the first mechanism is called gain of function. So this expansion, they can form this G-quadruplex complex, and therefore they can sequester some RNA binding proteins such as TDP43. or they can be translated into dipeptide protein aggregate, such as polyglycine arginine or polyglycine alanine, etc. So these two toxic species then will accumulate in the neurons and induce stress, and also are not eliminated in time to reduce their toxicity. The second mechanism is called loss of function, also directly from the patients. They have a reduced or decreased C9orf72 protein expression level. Therefore, it downregulates the physiological function of these proteins in the cells. However, the exact function of this protein is still not clear. And this is also the focus of my research, and try to use a structural and biochemical approach to answer this question. In 2016, multiple research groups, they used proteomic studies to find out what are the binding partners for C9orf72. In consistency, they found that C9 can bind with two binding proteins, including SMCIA and WDR41. And interestingly is that both of SMCIA and C9orf72 are belonging to a DIN protein module, and that they share a similar domain architecture that have an N-terminal login domain followed by the C-terminal and DIN domain. And WDR41 is a A-braid beta propeller, and this subunit can targeting the whole complex to the lysosome surface when the cell is in starvation. And many members in the guanine nucleotide exchange factor, or called GAF, are also reported to belong to a DIN protein module. So this GAF is an enzyme that can promote the GDP release from small g proteins. And therefore, because of the higher concentration of the GTP in the cells, and then these small g proteins, they can switch to their GTP bound state, that means the active state, and facilitate various of the membrane trafficking events. So our first next question is, of course, try to validate if indeed the complex can promote the nucleotide exchange activity for small g proteins. So we transferred these three components in the HEC293 cells, and also reconstitute them from the cells. We also prepare several candidates, including REP88 and REP39B, which were detected from the proteomic studies. And then we perform an in vitro reloading protocol and to load them into a main GDP bound state. And then we're following the main signal. So here shows a positive control of REP5 incubate with its GAF protein REPX5. There is a drop in the main fluorescence when we incubate these two proteins, and showing that REPX5 indeed can promote the main GDP release from REP5. But for the case of REP88 and 39B, when we supplement the C9orf72 trimer complex in the reaction, the signal remains the same. Therefore, based on this result, we conclude that C9orf72 with its binding partner cannot serve as a gap for these small g proteins. And this result actually more motivate us to achieve the structure of this complex that may bring us some hints about its function. Therefore, we apply our purified materials and then put them in the Titan Cryos with K2 camera. And in order to also increase the contrast, our data set was collected using faceplate. So the bottom here shows the 2D class FH for this complex. And you can see pretty nice, clear secondary structure features. And also you can see this nice donor shape of the complex. So from this data set, we managed to achieve around 3.8 angstrom resolution reconstruction for this complex. And overall, this complex has around 140 angstrom in length. And it also has isolic hook shape. And firstly, we assign the WDR41 of its obviously donor feature to the ring region of the hook. And the body part of the hook is comprised with two C-terminal and DIN domain. The two N-terminal long-in domain from C9orf72 and SMCRA, they dimerize to each other and also serve the tip region of the hook. And there is no direct interaction between C9orf72 with WDR41. And SMCRA using its C-terminal DIN domain in contact with WDR41. We also perform other extensively experiment to validate our this domain assignment. So after we achieve this structure, and then we compare our structure to other protein complex, which was already published in the literature. And actually, there is another double long-in DIN protein complex, which is follicular FNIP2 complex. However, this complex actually is a GTPase activating protein, or called GAP protein, that can stimulate the GTP hydrolysis. And this complex can specifically stimulate the GTP hydrolysis for red C or D, which is a subunit in heterodimer red GTPase, an important protein complex regulating the mTOR1 signaling. So the structure of follicular FNIP2 was also determined. And here you can already clearly see that follicular FNIP2 has a pretty similar structure compared to our structure SMCRA with C9orf72. And also there is one residue, arginine 164, located at the follicular subunit, was the cation residue that facilitate that characterize the GTP hydrolysis for its substrate. Once it is mutated to alanine, none of the activity was detected by using intrinsic tryptophan fluorescence. So based on their similar structure comparison, and that we then therefore propose that the SMCRA C9orf72 actually is a GTPase activating protein to promote GTP hydrolysis for its substrate. And more interesting is that the sequence alignment between SMCRA and folliculin show that a conserved arginine finger motif, and therefore which the corresponding arginine 147 in the SMCRA residue is maybe also the important catalytic residue for its activity. And then the next question we were interested to see is what are the substrates for this complex? So we go back to all the literature and found that in 2016, the center group, they published a paper in Nature Neuroscience, and they were also investigating the function of C9orf72. In their experiment, they showed that once C9orf72 is knocked down, the length of the exon is shortened compared to the control experiment. And then they did a more deep investigation and shown that once C9orf72 is depleted, there is a higher GTP F6 level. And F6 with is another family member F1 are two important small GTPase regulating the actin dynamic, the actin cytoskeleton dynamic. And it also is really redundant in the cells, facilitating different membrane and trafficking reaction. Therefore, therefore we prepare the F family members, including F1 and F6, and then use intrinsic tryptophan fluorescence as a readout to test if our complex indeed is a GAP protein. So here shows the wild type F1 incubate with the C9 OR72 trimer compress. There is a drop in the fluorescence, indicating the GTP hydrolyzed into GDP. And it is the same result when we incubate a wild type F6 with the C9 compress. But not the case with wild type F1 or wild type F6 with negative control and gap compress. And the dimer compress has similar efficiency compared to the trimer compress. And this result is inconsistent with our structure that WDR41 is located on the opposite side of the catalytic arginine residue. Once these two small G proteins are mutated into their GTP lock mutant, or the catalytic arginine residue are mutated to aniline, none of the activity detected. So indeed, from our intrinsic tryptophan fluorescence experiment, we can confirm that C9ORF72 with its binding partner can promote the GTP hydrolysis for F family members. Then we further imply another readout, which is HPLC-based gap activity. So we prepare two groups of reactions. One is just a small GTPS. One, we supplement our tested gap compress, and we incubate them at 37 degrees for 30 minutes. And then after the reaction finished, we just quickly denature the proteins while the nucleotide will remain stable. And then we just inject this supernatant into the HPLC, and then the result allow us to compare the signal and also the identity of GDP and GTP. So if indeed the gap compress promote can convert GTP to GDP, then the signal of GTP will either decrease or totally disappear, which in turn the intensity for GDP will increase.
Mignon, excuse me, you have
yes.
2 minutes to go.
2 minutes, okay. Yeah, so we use this HPLC-based assay to repeat our previous reactions. And then we've shown that indeed, from this HPLC-based assay, we got a similar result with the intrinsic tryptophan fluorescence. Only the wild type F1 or F6 incubate with our C9 compress, the signal of GTP disappear, which in turn, the intensity of GDP increase. And I may just quickly skip this. And the next goal of our research is we are interested to see how the C9 compress bind to its substrate. And we test a lot of different strategies, and they did not give promising result. And then we noticed that the N-terminal of SMCI actually quite dynamic. Its 50 residue is basically flexible, which may serve as a long linker. Then therefore we construct F1 to the N-terminal of SMCI8, and then we co-transfer it with another two components. And then we check the nucleotide identity with this for these chimera proteins, and it only showed the GDP signal. And with these proteins, we further incubate with a phosphate mimic compound beryllium fluoride, which can provide or to stabilize the gap small GTPase conformation. And indeed, we use these proteins, also apply it to the Titan Cryos. We collect enormous of data, including just the flat data set combined with two tilt data set. And eventually we managed to achieve a 4 angstrom resolution reconstruction, which allow us to dot the F1 crystal structure into the density. And here we just want to show that although our F1 in the chimera protein is GDP bound state, however, only while the F1 in its GTP bound conformation exactly fit into our density, it means that the beryllium fluoride indeed can stabilize the compress. Here just show that we also look into details of the active site despite they have different, totally different structure compared to other known gap proteins for this small GTPase, but they have a conserved arginine residue that points to the beta and gamma phosphate to stabilize this phosphate, allow water to act as a nucleophile to attack the phosphate for release. Yeah, so we indeed also just introduced the mutations at the interfacial between ARF1 and C9orf72 and SMCIA, and tested their gap activity read out by HPLC. And indeed, the residue that on the on C9orf72, which serves as a kind of lock, can hold ARF1 in place. Once they are mutated, their activity will abolish. So that you can see that the intensity for GTP still remain. So, okay. So I just also want to summarize that from this work, we firstly determined the EM structure of C9orf72 complex with its binding partner. We also confirmed that the complex cannot promote nucleotide exchange for small GTPase. We further, by structure comparison, we found that this complex may serve as a GTPase activating protein. And we also validate this by combining two assays. One is tryptophan fluorescence and also HPLC-based experiment. We further also determine another EM structure of C9orf72, which bound to its substrate. We also shown that the important region of this complex is the two N-terminal long-in domain serves as a binding pocket to hold its substrate. And also we demonstrate that the arginine 147 on SMCIA points to the active site and can facilitate the GTP hydrolysis. We finally also, using a mutation experiment, and confirm the important residue located at the interface between the complex. And there are still a lot of questions besides of the alpha family members just as a substrate for this complex. Actually, there is another group report that the complex can also facilitate the GTP hydrolysis for another two small G proteins, including RAP8A and 11A. And however, the whole complex, how are they located in the cells under different regulations, and how and when and how exactly they execute their functions, and still not clear. And that's why now we are pursuing more cell experiment and hope that we can provide more and details about how C9orf72 regulate the whole signal, and how, when it is defeated, how it correlate to the pathology in the ALS and FTD. So finally, I just want to acknowledge my postdoc lab, my postdoc training in the Hurley lab from UC Berkeley. I want to thank you, my supervisor, Jim Hurley, and also other Hurley lab members, including many senior postdocs who already start their own independent lab. I will also want to acknowledge the EM support and also our funding support, including AFTD and also DOD. So with that, I'm happy to take questions if there's still time.
Mignon, thank you very much for your talk, and I'm sorry again for those technical issues you experienced. And unfortunately, we ran out of time dramatically, so I'm very sorry I cannot accept any questions at the moment.
Okay.
But thank you very much again. Thank you.
Thank you.
And see you again on our conferences with new discoveries. Thank you.
Thank you.
Dear colleagues, I'm very happy to meet you at the 5th section of Russian International Conference on Cryo-electron Microscopy. And let me open our section named Structure of Viruses and Chaperonins with the first talk of Dr. Pavel Plevka. It's named Capsid Opening Enables Genome Release of picorna-like Viruses. Please, Pavel, you have 30 minutes.
Okay, hello everyone. Thank you for a kind introduction. And at the very beginning, I'd like to thank organizers of the conference for the opportunity to present here our results on the genome release and genome delivery mechanisms of picorna-like viruses. So I'll talk mostly about human enteroviruses with little help from honeybee viruses from the family Flaviridae. Human enteroviruses are a large group of viruses that cause various diseases. The most popular is the common cold, which is caused mostly by rhinoviruses. And every adult human is infected by them on average 4 times a year, while children are infected about 10 times a year. This is due to the fact that human rhinoviruses exist in hundreds of serotypes, many of which were identified, but many of which as well remain unidentified. However, enteroviruses are not only about the running nose, they can cause also bleeding, inflammation of the eye, hand, foot, and mouth disease, and in some cases, encephalitis, which is shown on this magnetic resonance image of a brain of 4-year-old child that has lost the ability to speak. In my talk, I'll present you some of the mechanisms that the viruses use to infect cells. So these viruses have non-enveloped particles with the diameter of about 30 nanometers, and they enter cells by receptor-mediated endocytosis. Once in the endosome, it's so far poorly understood how the genome is released from the particle and transported into the cytoplasm of a cell, where the genome itself, its positive sense single-stranded RNA molecule, can initiate the infection. The genome contains internal ribosomal entry site that recognizes a ribosome, and this leads to initiation of translation of the genome. It's translated as one long polyprotein that is then autocatalytically cleaved into functional virus proteins that induce reorganization of the infected cells. They induce formation of so-called virus replication factories that are derived from the membranes of endoplasmatic reticulum. And in these factories, the virus genomes are replicated and new particles assembled, and then they are released from a cell in the process of cell lysis. And in my talk, I'll focus on this step, how the genome is released from the virus particle, and then how it is delivered across the endosome membrane into cytoplasm of a cell to be infected. It has been established for a very long time that the genome release of enteroviruses proceeds through distinguished structural changes of the virus particle. So we start with an infectious virion that by binding to receptors and exposure to acidic pH in endosomes is triggered to transform into so-called altered or activated particle. And this process is connected to release of minor capsid protein VP4. Then the activated particles spontaneously release the RNA genome, and we end up with empty capsids. There have been numerous speculations how the RNA genome escapes from the virions or from the activated particles. The initial hypothesis was that the RNA may be released through channels along the 5-fold axis of the capsid, which are in native state of the viruses blocked by ions. However, it was speculated that some of the side chains may move aside and form a channel for a release of the RNA. This theory was abandoned because the channel is not big enough to enable passage of the RNA molecule. Later on, the technology enabled determination of the structure of not only of the native virion, which is shown here on the left, but also of empty and activated particles. And it was recognized that the capsids of activated and empty particles are somewhat expanded, and they contain channels along the twofold axis of the icosahedral symmetry. Then it was also speculated that these may be the sites for the genome release. However, even these channels are not big enough to enable escape of the single-stranded RNA molecule. And the situation is even more complicated because, as I mentioned, the genome is single-stranded, but it contains some special RNA structures, such as the IRS, internal ribosomal entry site, that contains complementary sequences, thus form double-stranded RNA, and these structures are probably present also inside the virions. And the mechanism by which this high-order structure would be unwound is not known. So we decided to look at the genome release of enteroviruses, namely of echovirus 18. This work was performed by David Buchta. He took variants of echovirus 18 and exposed them to acidic pH and then looked at them under cryo-electron microscopy conditions. And he could identify particles of 3 types. The blue arrows, they indicate particles in the activated state that have compact capsids and contain the genome. Then the yellow arrowheads indicate empty particles. And then there was a number of particles that were kind of half full, half empty, and associated with some extra density that we hoped may correspond to the genome in the process of escaping from the particle. Then David performed 2-dimensional classification because the individual electron micrographs are difficult to interpret. And from the 2-dimensional class averages, he immediately realized that there are capsids, that there are particles that actually miss parts of their capsids. And then we can compare these class averages to the individual particles that contributed to the class average. And here we can actually see some material that we think is the RNA genome that is escaping from the particles. So seeing this result, he could calculate asymmetric reconstructions of the particles. And he obtained 3 major classes of particles missing either 1, 2, or 3 pentamers of capsid protein protomers. So they are shown here, rotated 45 degrees. And the column on the right side is showing cross-section through the cryo-EM density of the particles, showing that the empty opening of these particles really doesn't contain the capsid proteins. It's the space through which the genome can escape. And this, however, raises the question, why do these particles open? Because these viruses are not like bacteriophages that contain their genome packaged under pressure. The genome here is single-stranded RNA, so it's much more flexible, and it's also not packaged under such high density as the genomes of bacteriophages. So where does the pressure to open the particle come from? So there are some indications. So when the particles of enteroviruses transform into activated particles, there are not only changes in the capsid that can be studied to high resolution using either X-ray crystallography or cryo-electron microscopy, but there are also changes in the genome structure. So if you look in the picture on the left, there are native variants, and you can see that the distribution of the genome inside the particles is uniform. In contrast, the genome appears to have some grainy structure in the activated particles on the right. And here, this comparison shows us that there is some change in the structure of the genome, but it doesn't provide evidence that the genome would be pushing on the capsid from the inside. So here I'll step away from human enteroviruses to honeybee viruses. We studied the structure and behavior of deformed winged virus of honeybees under neutral pH and then in acidic conditions. So the virion in neutral pH looks like this. It's a compact particles with some extra protrusions relative to enteroviruses. And here we cut out the front quadrant of the electron density so that you can see the density inside the particle. It's icosahedrally average density of the RNA genome. When the particles are exposed to acidic pH, they expand a lot, much more than the particles of enteroviruses. That's because the pentamers of capsid proteins are connected by rather long flexible linkers here. And in the acidic pH, we also observe particles that have released the genome. And you can see by the comparison of the coloring, because the surfaces of these particles are colored radially, going from blue, small distance from the particle center, to red, high distance from the particle center. And you can see that the particle that lacks the genome is much more compact. Most of the surface is green than the particle that contains the genome. So actually comparison of these two particles provides evidence that the genome in the acidic pH starts to push on the inside of the capsid and wants to open it. So with this information, we partnered with the group of Robert Vacha, who performs molecular dynamics simulations of coarse grain models of virus particles. And they could find conditions in which, after some time of simulation, with the genome pushing on the inside of the particle opens like a Pac-Man. And in this process, in some cases, one or a few pentamers of the capsid proteins are broken away from the particle. So the capsid still has, the capsid proteins, they still have affinity for each other. So eventually the capsid closes and the release of the genome is completed by diffusion of the RNA from the particle. Overall, this process is very fast. Here you can see the time scale. So the genome release through this particle opening and then diffusion through the hole formed by removal of one or a few pentamers is in all cases finished within a microsecond. And it's likely that actually this high speed of genome release is beneficial for the viruses because it reduces the time that the RNA would be exposed to degradation by RNases that may be inside the endosomes. So it was interesting to see this type of genome release for echovirus 18. And to make the conclusions a bit more general, we looked at asymmetric reconstructions of particles in the process of genome release of also echovirus 30, human rhinovirus 2. This was actually published by a group of Dieter Blaas, and slow bee paralysis virus, that's IFLA virus that infects honeybees. So this particle opening actually appears to be quite general mechanism used for genome release of numerous viruses that belongs to the order of Picornavirales. So from here, I'd like to move to the aspect of summarizing the, the process of genome release. So as has been shown a long time ago, the native variants, they transform to activated particles. Then these particles open, and in this process, they may lose a couple of pentamers of capsid proteins. So we end up with these open particles through which the genome can diffuse. And if we are studying this process in vitro, these detached pentamers may reattach to the empty particle. So we end up with complete shell. So now I'll move to the study of the process by which the viruses ensure that once the genome is released from the particle, it is delivered into cytoplasm of a cell. Because the virus, even if it is endocytosed, still needs to deal with the fact that it's enclosed in a membrane and the cytoplasm is not readily accessible. So to study this process, we used cryo-electron tomography. And take the advantage of the observation that COS7 cells, which are like mammalian fibroblast cells, when grown on a grid for electron microscopy, form these flat lamellipodia that are transparent for electrons. So when we look with low dose, low magnification image, we can see this peripheral part of a cell that is electron transparent. To select areas for data collection, we record higher resolution collage of images that enable us to see roughly what features are present in the whole of quantifoil, where we can record data with good contrast. So when we look at control cells, we can see endosomes here. The endosomes can be wrapped with single or multiple membranes. And the surfaces of these endosomal vesicles are in most cases smooth. In contrast, when we infect the cells with enterovirus, we observe what we call membrane warping. So the surfaces of the endosomes are no longer smooth, but they have this concave curvature. You may not see the virus particles at first in these projection images. However, we can also collect tomographic tilt series and calculate tomograms. And here I'm showing you a section of the tomogram in which the individual virus particles nicely stand out. And using the tomograms, we can also determine that the virus particles are actually inside the endosomes, that they are not sitting at the surface of the cell. So now the question is, what actually enables the viruses to reach the cytoplasm? And when we wait a little bit longer after infection, when we look into the cell, this process of membrane warping of endosomes becomes very extreme, and it actually leads to disintegration of the endosome vesicles, and their content is spilled into cytoplasm. So we are now working on identifying what is actually causing this endosome warping and disruption. And we think that the virus actually overactivates some signaling pathway and overactivates some membrane remodeling machinery of the cell that leads to disintegration of the endosomes. This is because in about 10% of endosomes from control cells, we also see this membrane warping. So when collecting the projection images of infected cells, we can actually use these pictures, these images of the individual particles to calculate three-dimensional reconstruction using the usual single particle reconstruction approaches. And by this, we can determine that actually most of the particles inside the endosome and even in the cytoplasm are in a native conformation, whereas the particles that look like rings, they are highlighted in red here, are empty. So in this analysis, we could not identify any activated particles, which indicates that in vivo, they are very short-lived intermediates, and the virus particles immediately release the genomes. This brings me to the summary of my presentation of the infection process of picorna-like viruses with particular focus on enteroviruses. So these viruses, they bind to the receptors. This triggers some signaling into a cell, leading to endocytosis. And these endosomes that contain the virus particles are subject to some membrane remodeling machinery. The surface of this endosome is warped and eventually disrupted, which leads to release of the virus particles into cell cytoplasm. Then these particles transform to activated particles and immediately release their genome, and the infection can be initiated. And with this, I'd like to thank members of my group, namely to David Buchta for his work on the genome release in vitro, Aygul Ishemgulova for her work on analyzing the genome delivery process in infected cells, and to Karel Škubník, who worked mostly on the honeybee viruses. I'd like to also thank to SEITEC and Masaryk University and to our funders. And thank you for your attention, and I'll be happy to answer any questions.
Before I give the right to ask the questions to the audience, I'd like to ask a few questions by myself, if it's possible. What is the pH level that is enough to activate the particles?
So this is, so first of all, there are two aspects. So many of these viruses, they require a receptor binding that triggers some conformational changes that renders the particles actually sensitive to the pH change. And then the genome release can be induced at pH 6 or 5.5.
Yes, so it's easier to reach this level of pH in the endosome, I guess.
Yes,
Not after the viruses are released into cytoplasm. So they are not getting activated within the endosomes, and they transform to short-lived activated forms after the breakup of endosomes, right?
Yes, so these results were surprising to us because it doesn't conform to the established theory. So what we think is happening is that the virus is like predisposed for transformation to the A particles by binding to the receptor and some acidic pH in the endosomes. However, we think that these are the early endosomes, so not too acidic. And then as the viruses are released from the endosome, they are exposed to different ion composition than that was inside the endosome. And we think that it's this actually not so much pH change, but ion composition change that triggers the genome release.
Yes, and activation is also connected somehow with loss of one of the proteins, right?
Yes, the minor capsid protein VP4 is released.
Well, no. Thank you. Please, your questions now. People from audience, we have nothing in the chat. Any questions? So, Olga Sergeyevna, please.
Thank you very much for a very interesting talk. And do you have any idea which membrane machinery this virus will organize to make these non-even membrane structures?
Mm-hmm. Well, so far we do not know. We are in the process of testing various inhibitors of this membrane remodeling. So it could be like the escort pathway. However, there are several like alternatives membrane remodeling systems that could be involved.
Yes, because we were studying together with Brandeis University. We were studying the membrane modeling by NVK, nervous rag, and other proteins that are they have these F-bar domains, and we got very similar figures of just giant liposomes. So I'm wondering if something similar to this F-bar or I-bar domains are also involved in this case.
Yes, well, it's possible. At the moment, we unfortunately do not know. But thanks for pointing it out.
So, more questions, please. So, if there is no questions, I have one comment, perhaps. Lowering the pH activates the particles, but at the same time, lower pH means less charge on phosphate groups of RNA. So there is less electrostatic repulsion between charged phosphates of sugar phosphate backbone of RNA and less pressure of genome from within, I guess, from the regular standpoint of a physical chemistry, right?
Yes. So this is a very good point, and we were also confused because when you actually lower the pH, there's no reason why the genome should want to escape from the particle. On the opposite, it should be more happy, even more compacted. So in these viruses, the charge of the RNA is neutralized by polyamines like spermine or spermidine. So it's possible that actually the exposure to the acidic pH disrupts this interaction. The polyamines, some of them may be released from the particles, and this could lead to the repulsion.
Yes, or maybe the higher ionic strength, for example, or ionic composition, as you've already noticed in your study, maybe it does something with those forces within the capsid. So we have to find a way to measure the pressure, and that would be a nice follow-up for this amazing work. Thank you, Pavel.
Okay, thank you very much.
Thank you. So we have to take a technical pause for a while before we introduce the next speaker. And this is unfortunate.
Lepší?
Yes, we hear you. So 15 minutes, please.
Okay, I will start then. Hello, my name is Marta Šiborová, and I'm really happy that I can present on this conference some results of our recent work on bacteriophage SU10. So today I would like to introduce you this phage, its structure and mechanism of genome delivery. Bacteriophage SU10 belongs to family Podoviridae, and it infects E. coli. It has a large 77 kilobase pairs long genome, which is packed in a long virions, which have a length of 145 nanometers and the diameter or the width about 45 nanometers. And on one of the vertices, there is a short tail, which is decorated by long fibers, which are quite similar to those of bacteriophage T4. We were able to induce the genome release from the virions. So on the right image, you can see the virion, which is almost empty, but there is a last layer of DNA retained inside just under the capsid. Bacteriophage SU10 has a latency period of 47 minutes and a burst size of 166 new phages. It means that 47 minutes after the infection, one cell can produce almost 170 bacteriophages, which are ready for new infection. We visualized the infection of E. coli by bacteriophage SU10 by tomography, cryo-electron tomography, and fluorescent microscopy. So here on the beginning of infection at 5 minutes, you can see the cell, which has several phages with capsids which are still filled by DNA attached. And in corresponding time in fluorescent microscopy, you can see the bacteria, which is red and blue, which is decorated by green phages. Their DNA was stained in green, so the phage DNA gives the green signal. Further, during the infection, we can see that empty phages are still attached to the bacterial surface. However, in the fluorescent microscopy, we can see how this green signal was transported from the outer part of the bacteria inside, and now it nicely colocalized with the blue bacterial DNA. Later, at 45 minutes, which is just before the expected burst, you can see there are new virions being assembled inside of bacteria. It corresponds to this granularity which is forming inside of the bacteria and which we can observe by fluorescent microscopy. To understand more how the bacteriophages attach to bacteria and how they release its genome to the host, we solved the structure of native and also of genome releasing bacteriophages. Native virion, you can see the capsid in the turquoise, and on a cross section you can see the DNA and also the core proteins filled in the capsid. The DNA creates these nice concentric layers, and on one of its 5-fold vertices there is a portal complex attached and the rest of the tail. So bacteriophage SU10 has a portal with a long barrel domain on its top, and most of the portal is hidden inside of the capsid. The rest of the tail is exposed out of the capsid, And to the portal, there is a dodecameric adapter complex attached. And also this adapter complex is harboring 6 pairs of the long tail fibers. Here you can see the long tail fibers in purple, but only its N-terminal part was resolved, but they continue as a very long arms, similar like in bacteriophage T4. To the adapter complex, there is a tail complex attached. It's a hexamer, which is decorated by short tail fibers, which are pointing up in a native virion, and from the center of the tail needle is protruding. If we compare native virion with genome releasing virion, we can see the layers, last layer of DNA, which is still in the capsid of the genome releasing particle. And there are also major changes on the tail of the bacteriophage. Due to some time restrictions, I will not describe all structure of whole 32 megadalton virion, but I will focus mostly on the tail, which is in red, and on the green short tail fibers. Monomer of the tail protein can be divided into 4 domains. One of the domains is platform domain, and in this domain, C and the N-terminal part or regions of the tail protein are meeting. In the core of the protein, there is a beta propeller with the fiber domain, and this fiber domain is actually holding the short tail fiber. And there is a insertion domain or domains, nozzle domains, which are connected to the beta propeller. If we look to the beta propeller in more details, you can see it has say 7 blades, and on blade 4 and 5, there are loops which are providing interaction, which are oriented to the center of the tail and which are interacting with the tail needle. Between blade 6 and 7, there is an insertion where actually this nozzle domain is, and on the blade 1, there is a fiber dock. Let's have a closer look to the fiber dock. So here we are looking at the fiber dock from the bottom, and in order to harbor the trimeric short tail fiber, monomeric fiber dock mimic threefold symmetry. It provides 3 tryptophans, which are pointing up to the center of the short tail fiber, and the short tail monomers of short tail fiber are providing 2 tryptophans and 1 isoleucine, which are zigzag interacting with the protein chain of the fiber dock. So this is how the short tail fiber is interacting or holding on the tail of the bacteriophage. If we combine the monomers to the actual complex of the tail, on the upper right you can see the side view, and on the lower right you can see the bottom view. It creates the hexameric cone-like structure. The nozzle domains of tail are actually hugging the beta propeller of the neighboring domain, and they are supporting the short tail fiber from the neighboring domain with this terminal part of the nozzle domain. Here you can see the loops from the beta propeller, which are actually facing to the center and which harbor the tail needle. If we compare the phage tail of the native on the left side and the genome releasing particle on the right side, we can see there are some major changes, and relatively short tail, which had like 11 nanometers without the tail needle, get elongated to 28 nanometers, and now the short tail fibers are actually flipped down, and they alternate with the nozzle domains, which are remodeled, and also they are facing down. So this is how the remodelation may look like. The fiber dock loop flip like a pancake, and it brings the short tail fiber with it down, and it aligns with the nozzle domains. We also wanted to see if this structure corresponds to the real situation on the cells. So we made some single particle reconstructions of the tails of the bacteriophages, which are attached to the bacteria. Here you can see the phages which are interacting with bacteria approaching from the side, interacting with the fibers, and this one is already sitting with multiple fibers bound to the surface. And on the right side, there is a slice from the tomogram with several phages bound. Two of them are empty, one is full, and this one empty, you can see there is a tube which is going through the both membranes and cell walls, and it's ending in the cytoplasm. So all of these results together allow us to propose the mechanism how bacteriophage SU10 interacts with the cell and how it delivers its genome. So bacteriophage, which is native, it still has the capsid, which is filled by DNA and core proteins. It approaches from angle to the bacteria, and it bounds by these long tail fibers to the outer membrane. There are primary receptors at the distal ends of the long tail fibers. When all the fibers bound, it forces the arms of the long tail fibers more up towards the capsid, and it breaks the interaction with the green short tail fibers. This allows the short tail fibers to reorient, and in the same time also the nozzle domains of the tail reorient, and they create this alternating nozzle. Then the short tail fibers, which has a secondary receptor, bind to the outer membrane, and this binding forces the tail needle to go through the outer membrane. Then the tail needle dissociates to periplasm and the channel through the portal, and the rest of the tail machinery is open and material from the capsid can be released. First, there is a release of core proteins, and one of these core proteins has transglycosylase activity, which allows degradation of the cell wall, which is under the outer membrane. Together with our core proteins, it assembles through the periplasmic space to the channel, which allows the phage genome to be injected to the host cell. With that, I would like to thank you for your attention, and I would like to thank all people of Plevka Lab, especially to Míša Procházková, Tibor Fuzík, and Pavel Plevka, and also to Anders Nilsson, who isolated the phage and provided it to us, Martin Benešík, the local phage master, Jirka Nováček, the head of CETEC Cryo-EM facility, and Ondra Šedo from Proteomics facility. Thank you for your attention.
Nice talk. I got a couple of questions, if you please. So what is known about the receptors, the receptor moieties on the surface of the host cells supporting the infection by this phage?
Receptors on the cell surface. Well, since this is E. coli bacteriophage, these receptors are expected to be quite similar to other E. coli phages. And also the receptor binding proteins on the phage itself were not resolved. So we have only some predicted structure similarity models.
Mm-hmm. I see. So on the short tail fibers, can you predict any of the conservative protein domains, like enzymatic domains or lectin-like domains?
No, because we did not resolve actually the part where the receptor is. We resolve only the N-terminal part.
But this can be done on amino acid sequence level. So
yes, but there is not many homologs.
I see. So it's one more interesting point. So please, more questions.
bacteriophage more at the site of bacteria or at the tip, or they don't have any preference where to attack?
This bacteriophage does not have any preference. It binds all around the bacteria. It does not care about any flagellas or pilies as some other phages can.
Have your question, your question answered? Yeah, thank you. More questions, please. So there is no questions more. I'll check in the chat. No, nothing. Thank you. Thank you for very interesting work. The biology is combined with the structure in a very logical way. Thank you, Marta.
Thank you.
Thank you. Hello, hello. Can you hear us? Yeah. Great, great. I'll have to reintroduce the next speaker. This is Dr. Marina Serna with a talk named Cryo-EM Structure of the Reconstituted Human Gamma Tubulin Ring Complex. Please, you have 15 minutes.
Let's start by thanking the organizer for giving me the opportunity to present my work today here. So let me see. Okay. Well, I have some problems. I cannot move it. Oh. Okay. I don't know why, but one slide is a skip, but doesn't matter. I wanted to tell you that the microtubules are essential polymers in the cells that are very important not only to confer the cellular structure and shape, but are also key in cellular processes such as cell division, intracellular transport, and cell migration. They are polarized polymers made up of alpha-beta tubulin heterodimers. And one of the most important features of the microtubules is that they are quite dynamic structure that can be assembled and disassembled very quickly in the cell upon the cell requirements. Most of the microtubular functions and many of their features are regulated in part by the centrosome. In fact, in animal cells, the major microtubule nucleate or center is the gamma tubulin ring complex or gamma TARC. This is a multi-protein complex embedded into the pericentriolar material of the centrosome, and it has been proposed that it serves as a template for the alpha-beta tubulin heterodimers to polymerize into the microtubules. So with all this information in mind, we wanted to set up a recombinant gamma TARC expression and purification system in order to try to analyze the structure of this complex and to get some insight about its assembly and its regulation. In the lab, we have been working for many years in a protein complex composed by the AAA ATPases RABEL1 and RABEL2. This RABEL complex is involved in the assembly of many macromolecular complexes and also very diverse macromolecular complexes, and we have demonstrated to be so for the gamma TARC. When we deplete RABEL1 in HeLa cells, these cells display defects not only in the central duplication, in the mitotic spindle formation, and in the chromosome congression, but also, and very importantly, in the assembly of this gamma TARC complex. This information turned out to be critical for us to set up this in vitro recombinant and expression system. So all the components of the gamma TARC were co-expressed in insect cells infected with a recombinant baculovirus. We observed that the presence of this RABEL complex was not necessary for the expression of the gamma TARC components or to maintain its stability. However, this RAB complex was critical to be able to obtain a fully assembled gamma TARC complex. This sample was then used to vitrify and analyze its structure by cryo-electron microscopy. We finally get a reconstruction of with an overall resolution of 4.2 angstroms resolution. So this structure is an open ring, and we immediately realized that the resolution of this structure and this reconstruction was quite anisotropic, and most of the flexibility of the complex was focused at the seam of the ring. So we decided to apply a divide and conquer strategy in order to focus the refinement in different small subvolumes of this, or small pieces of this map. And by doing so, we significantly increased the resolution for most, if not all, the small pieces of this complex. So this is the structure of the gamma tubulin ring complex, and as you can see here, is composed by 14 subunits. Thanks to the resolution of this structure, we were able to identify all the individual components of the structure and also to define the stoichiometry of this complex. Its gamma TAR component is composed in turn by 2 GCP proteins. Each GCP protein is bound to one monomer of the gamma tubulin. And the organization of these GCP proteins in the gamma TAR complex allow the formation of one helical turn of this gamma tubulin that it could serve as a template, as it was proposed before, for the alpha tubulin heterodimers of tubulin to form these microtubules. However, one of the most striking features of this structure is that it presents this helical deviation that prevents it to become a perfect template for the microtubules. By the time we were working with this structure, 3 different structures of the native gamma TAR complex were reported. And it was for us very good to check that this native gamma TAR structure has the same protein composition and the same stoichiometry. And moreover, all of them present this helical deviation that prevents the complex to become a template for the microtubules. So this suggests that maybe there are additional factors, or maybe this complex has to undergo a conformational change to become fully active. Thanks to the resolution of the structure of this recombinant gamma TARC, we were able to see also some additional structural elements. For the sake of time, I cannot go into the details, but what I can tell you is that some of these elements were also identified the native structure, and we were able to assign the identity of the protein. And while others were only observed, probably due to the resolution differences in our recombinant complex. All these structural elements seems to be related with the assembly and the stability of this complex. Okay, so if I understood it well, I can resume the presentation here. So this is the slide where it stops. I don't know why. So in this slide, I was just telling that we were able to, just by visual inspection of the complex, we were able to identify the protein composition and the stoichiometry of the complex. And I was mentioning that these gamma TAR components were composed by 2 GCP proteins, each of them bound to one gamma tubulin monomer, and the disposition or the organization of these GCP proteins in the gamma TAR complex allowed the formation of one turn helical placement of these gamma tubulin monomers in a way that this complex could become a template for the microtubules to be assembled as it was proposed before. However, one of the most striking features of this complex is that it presents this helical deviation that prevents it to become a perfect template for the microtubules. By the time we were working with this structure, it was published in 3 different papers, the structure of the native gamma TAR complex. And by comparison between the recombinant and the native gamma TAR structure, we realized that the protein composition and the stoichiometry was identical, and also that this helical deviation that we observed in the recombinant gamma TAR was also present in the native structure. So this suggests that maybe other factors, or maybe this protein has to undergo some conformational change to become fully active. thanks to the resolution of our structure, we were also able to see some additional structural elements that seems to be related with the assembly and the stability of the complex. For the sake of time, I cannot go into the details, but what I can tell you is that some of these extra densities were also observed in the native structure, while others were only observed in the recombinant complex. But I think this has to be with the resolution of the complex more than with the difference in between those complexes. And finally, we would like to understand the role of this radial complex in the assembly of the gamma TARC. We have proved that this complex is important for the gamma TARC to be assembled both in vivo and in vitro. But when we wanted to analyze this structure, the structure of the gamma TARC radial complex, we couldn't see any particles in the sample unless we add some chemical cross-linking to it. So it must be a transient complex. But by doing so, we were able to get a low resolution negative state map of this complex between the gamma TARC and the radial. And currently we are working to try to improve the resolution of this complex by cryo-electron microscopy. So finally, I would like to thank all the people that has been involved in this project, especially to the PI of the group, Oscar Yorca, and our collaborators are the IRB in Barcelona, Jens Luders and Fabian Zimmermann. Of course, thanks to the funding and to all of you for your attention. And I'm happy to take any question.
Thank you. Thank you for a very interesting talk. Due to our being out of schedule, I usurp the right for one question by myself. So why this complex is important from practical viewpoint, apart from its being pretty?
You mean why it's important, the recombinant complex or the gamma TARC in general?
Why do we need to study its structure?
Yeah, because it's not, the assembly mechanism is completely unknown for this complex. So this complex is composed by many different proteins, and it's not known how these proteins assemble and what is the regulation for the assembly of this complex. And I think the assembly of this complex is key in many important cellular processes like cell division. So by controlling this process or understanding the regulation of this process, of this assembly process, we can get a lot of information about other cellular processes, about the regulation in time and space, about these dynamics of the microtubules.
So it's relevant to a number of other questions.
It is.
Yeah. Thank you. Thank you again.
Thank you very much.
Thank you.
Thanks.
And now, dear colleagues, we have to head for our very short and timely coffee break. We'll be back here at 3:15. Thank you. Introduce the next speaker in our section. And this is Dr. Elena Orlova with a talk named Structural Organization of Syphovirid FH, SPP1, from its head to toe tips. Please.
Structural organization of Syphovirid FH, SPP1, from its head to toe tips.
And you have 30 minutes. Thank you.
Hello?
Yes?
Can you hear me?
You have 30 minutes.
Sorry. Hello? Do you hear me?
Yes. Can you hear me?
Yes, we do.
Can you show my presentation, please?
Sorry.
Сейчас начнем все сначала.
Ничего.
Презентация исчезла. Окей. Sorry. All right, I don't know if I don't hear anybody, but I hope you can hear me. At last, something you will tell me. It's a bit funny. All right, firstly, I would like to thank you for the nice invitation, give a talk on the viruses and some sort of bacteriophages. My talk is nearly the third one about the bacteriophages and the viruses. And in general, I'm not going to tell you about much of procedure and some kind of processing methods. If you want, please send me questions and then I will answer you after that. But in general, what I'm trying to explain to you, the achievements and how we're progressing and the understanding of the bacteriophages function through the understanding of the structures and different achievement during the many years of researches of this bacteriophage. Number one, why we want to analyze bacteriophages? We know that a lot of bacteria cause diseases, and diseases have to be fight, and it's a very difficult procedure. And mostly the most advanced approach was, and you have heard yesterday quite a lot about antibiotics and how antibiotics are blocking ribosomes to prevent the multiplication of bacteria within our organism or other animals. On this level, you can imagine that the antibiotic resistance is a very important issue. So if antibiotics they do not want, and developing new antibiotics cost a lot of money nowadays, and possibly we need to find another methods how we can find the bacterial diseases caused by bacteria. In these cases, we can use very natural enemy of bacteria, viruses, which exclusively and explicitly damage bacteria. And those are the bacteriophages. That's why we have to understand the specificity and understanding the function of bacteriophages, specific viruses, which will kill bacteria. So, important part that that viruses, bacteriophages, they cannot replicate themselves without bacteria. And most important part that they're bacteria specific. There are some certain different phages, how they can be virulent and they can be lysogenic cycle when they can hide within the bacteria and they can multiplicate with bacteria. We don't like these bacteriophages, but on this case, we need to find how to make them more lytic when they will just die together with the host bacteria, and how to make them specifically aimed for the specific point of bacteria. Typically, the number of progenesis in cells about 50-20 when one bacteriophage will infect the bacteria. How we can understand what's going on? We have to use electron microscopy, we have to use structural methods, and then we have to modify bacteriophages, and this how we can use them and to use for the many other medical aims. We have quite a number of different bacteriophages. In Cauda-viridalis family is most important to understand that the DNA viruses. And we have nearly 96%, 90% of all bacteriophages which we know so far that they are based on the DNA genome. much more important, another issue, that those viruses then have general three families: myviridae, cypheviridae, and podoviridae. Myviridae, mostly it's a T4, one of the most studied bacteriophages, and it has been studied quite a lot by the mutual research by Professor Messerginov and Michael Rossman. They have spent a lot of energy to study that, and now it's quite a lot done by Peter Lehman, who is in Galveston. Cypheviridae is few more phages they have been studied, and mostly they have been studied in France. It has been studied in America, and we have spent quite a lot, my group and the group by Paolo Tavares, on analysis SPP1 phage. And podoviridae has been studied, and there nearly only one capsid which has been resolved by X-ray analysis, and it was provided for us quite a lot important information which we are still using in analysis of all these phages. In general, what we know about that? It's based right now on the example of SPP1 bacteriophage, and this is a biochemistry of it was analyzed in very much details by Dr. Paolo Tavares in France, with whom I have a very close collaboration. And that's the idea, but in general, it's quite similar to all other tailed bacteriophages. We have a very specific capsid protein. We have a scaffolding protein, and there is a GP6, or it's only for SPP1, major protein, around which is provoked the self-assembly of the capsid within the host cell. Keep in mind that these bacteriophages, that's why it's important to analyze them, they're using the resources of the host cell to be self-assembled. And when they're assembling that mostly it goes and forms the procapsid, which is a reddish squarish here, and shown that one is a scaffolding which make the shape of the bacteriophage. And then with help of the terminase 1 and terminase 2, the DNA it's attached to the portal protein, and it will pump the genome inside of the capsid. When it goes inside of the capsid, then it make the high pressure inside of the capsid, and then it's except after that nearly some kind of it was supposed from the roundish shape into icosahedral shape. And the portal protein and terminase complex formed a very specific DNA packaging machine. It's an interesting and powerful motor which based on the usage of ATP, and it pumps DNA inside in a very well-ordered system. But when the DNA has been ordered, this door, so-called gatekeeper, has to be closed. For this, we have additional protein like adapter proteins and the stopper proteins. And then the tail, which is assembled in a separate way, will be attached and to make the entire infective bacteriophage. And when progeny formed in the host cell, they will burst up and the host cell will die completely. But these phages, new progeny, they are ready to infect other adjacent bacteria. That is quite important and essential steps of this development pathway of maturation of bacteriophage, which we are using in analysis and understanding how the bacteriophages are assembled. Here, you can imagine, as soon as we have blocked the activity of terminase N and 1, we have two steps. SPP1 procapsids, you can see it here. And then we have SPP1 bacteriophages, which are fully assembled. It's very good images, but because it's very good images and it can see inside of DNA of these bacteriophages, you can hardly see, but possibly you will be able to see this trace, which is the tail. Tail is about 160 nanometers in length, and it's quite long. It's very important part of the bacteriophages. Let's go how the bacteriophage is organized. Keep in mind that here, for example, this is a capsid. Let's go through its organization. We have done the organization and analysis of the procapsids at the very beginning, and it turns out, to our surprise, that this bacteriophage doesn't have only one type of procapsid. We have a small procapsid, big procapsid, and then we have a mature capsid. You can see that we have obtained pretty reasonable resolution, but we can assess that, for example, in the small bacteriophage, we have more scaffolding proteins. Here it's much less, but here the capsid is filled up with genome. What does it say to us? Look, we can see the conformation and possibly this intermediate, the new procapsid which we have found, it's something interesting which could provide us additional information. This is a small procapsid which is full of scaffolding. And here we have a quite big gap in the hexamers, and hexamers, they do not have a six-fold symmetry. And this is these symbols like red pentamers or sign triangles, they show with a special symmetry of the icosahedral. This is an independent part of this icosahedral system. And you can see how it's going on. That here, we have a big gap. This gap, it became nearly hexameric because the diameter of the procapsid is close to the fully assembled capsid, but here the hole is closed. But what does it say to us when we are coming on the atomic level? Because resolution about and angstrom allows us to trace the polypeptide chain of the channel, and we are able to see and to look what's to trace the chain. This is a chain which has been traced for SPP1. This is a chain which obtained by X-ray analysis for the P22 by the group of sorry. Suddenly I've lost the name, in America, and then we are able to trace the major, and it's very important part of spine helix alpha 3, which can see as a ring 1. And then we can say there's this general elements, E loop, we have an arm which goes, and that's it. These elements are quite important to us to understand how all these amino acids are assembled. Jack Johnson group X-ray analysis of this HK97. And you can see, but these the amino acids or amino acid lengths of this SPP1 is slightly longer compared to the HK97. And if you will compare the overlay of one of the subunits, we can see additional amino acids insertions which are existing in the SPP1. And they're sticking out, and it's provide the additional combination, etc. But moreover, we have a different position of the central loops which are within pentons, etc. More right now, let us have a look the transition from procapsid 1 to procapsid 2 and mature capsid. You can see that it's really expanded, and how this opening is here is became closed in the mature capsid. But this is mostly some kind of a dynamic of the process. But now we have to understand what's going on, what's with the procapsid, with the scaffolding. It was a really small discovery in the process of a development of bacteriophages, when it turns out that previously the idea was when DNA will be packed inside of the mature capsid, inside of the procapsid, it will be DNA which would push out of the procapsid scaffolding. But our experiments and analysis of the procapsids of nearly in natural environment of procapsids, it turns out the scaffolding slowly goes out of the procapsid and the procapsid 2. It has a nearly size of the mature capsid, and it really only has a scaffolding nearby the five-fold axis vertices. And it turns out that it's really became nearly empty already, and the pumping protein pumps DNA inside without requiring much less energy, because the scaffolding protein already has gone. So it's much easier for the portal protein and the pumping machine to pump DNA inside of the capsid. Now, this is, I would like somehow to emphasize the idea what was going on with our analysis in sense of the development of the technology and effect of the technology and new microscope in sense what we can achieve in analysis of the details of the portal protein. It's a just demonstration how it's useful to have a new technology, new software, new sample preparation, and how our achievements has been progressed in sense of the understanding of the structural features, in a sense of the activity of the molecular machines. In 1995, we had such a 25 angstrom resolution and a negative stain. Keep in mind, this is a naive organization which had structures in sense of when it's no other proteins were absent, and to our surprise, SPP1 portal protein has a certain fold symmetry. But you can see how the resolution was progressing. We have got the 20 angstrom resolution in 99. In 2001, we have 12 angstrom resolution. And then in 2003, we have got the 9 angstrom resolution. And for the first time, we were able to trace the locations of the alpha helices. But now, in 2018, we have got the very first reconstruction at resolution of the 2.7 angstrom, and then we are able to trace a lot of not only amino acids, we were able to find the conformational changes which are happening according to self-assembly within the native environment and self-assembly process. Look at that, what we are going right now. We have got this structure, and we are able to identify and to trace at de novo tracing of all this chain, GP6 portal protein, which was accepted, which was combined by GP15 adapter and GP16 stopper. Much more interesting, when we have done this analysis, for the first time, we have found our own inaccuracies and in not quite adequate analysis of the structures we have done previously. I will tell you about that slightly later. But nonetheless, keep in mind that at this level, we are able to trace the beta layers in the wing. We were able to see DNA loops which we had not seen before, and we have seen the very good, nearly all amino acids. Actually, we have seen nearly all amino acids within the entire structure, except the very edges and the periphery of the structure. Let us compare, because the structure was by X-ray analysis by Fred Anson and Andrei Lebedev in York a while ago, but this is a naive structure, and what was done, and it became to some extent classical description together with the reconstruction X-ray structure of 529 portal protein in the group by Michael Rossman. And then the very first, a general description of the structure has been described like a crown, the wing, the stem of the structure, and the clip domain. If we will compare the structure of the EM, which is in the light blue on the left, and we will overlay that, we can see that the core of the structure, like wing domain and the so-called spine structure of the GP6, helix 6 in the major arrangement of the portal protein, it's really didn't change much. But the most significant issues are related so-called in clip domain. If we will do that and we will check that, we have significant changes about the changes in sense of the, and it's important for the interaction and how the interaction with other protein change the way of oligomerization interaction with a different protein. And here you can see that the clip domain has been changed significantly. And here, when this alpha helix 4 moved up, it's moved about the 7 angstrom and rotating a good 35 degrees, you can see that it makes the pocket when the C terminus of the another adapter proteins goes inside and makes it tight. It's so effective that it's really, with a complex GP6, GP15, GP16 became much more significantly tight, and it's really nearly, you cannot dissolve that. Why was going on? The structure of GP15 and GP16 has been analyzed by NMR, and it has been done in France by Sophie Zinn, and she did very good structure. But the point is, what I'm trying to assess here, that explain here, that we have this EM structure, which quite different, but it's not, how to say, a new one. You can see that the loop between A3, A4 became like a hairpin. And what is interesting, the X-ray of HK97 GP6 13-mer adapters, but it was in isolation. It has a very tiny hairpin as well, but it was interesting that it has been observed within the X structure in 13-mer. But in our case, when we are looking at the structure, we see that it's really make the tube. And what is important, that this tube makes a link with the next GP16 protein, which is plays a role of a stopper. Why these two proteins are so important? That's exactly when we were analyzing the X-ray NMR structure of GP16. It was as well done by Sophie Zinn, and she was shown that this is a very flexible part. But when it goes into the complex with GP16, GP15, and GP6, this is it has quite serious refolding. With Urichiban, we have done a very complex structure, which I will show you slightly later, but it was suggested, and we were trying to analyze the symmetry, and the very first approximation, the very beginning, we thought that this is a 12-mer dodecamer as well, like the GP15 and GP6. And Paula Tavares made quite a lot mutation, that we have such glutamic acids. We have, for example, the glutamine and tyrosine, which are actively involved. And we have, if we will mutate them, the stopper doesn't work anymore. Is there such a connector with such mutation is not able to hold DNA inside of the capsid. But when we have done high resolution at the 2.7 angstrom of the entire complex, what we have found doing the de novo tracing, that inside of this channel, we don't have anymore this beta barrel. We have a barrel of 6 alpha helices. And more importantly, what you can see on the very right picture, that these amino acids which have been indicated here, they're still active, and they just indicate the interactions between these alpha helices. The mutagenesis analysis indicated that this is absolutely important information, but the organization from the three-dimensional structural elements, it's really different. It's not beta sheets, it's alpha helices, which makes, and the stopper still works as it is because it's only 12 angstrom in diameter as a whole. It holds DNA, and possibly this interaction of these alpha helices, they're much more stronger and they're really able to hold the high pressure of DNA inside of the procapsid and do not allow to leak it away. But on this level, if you will look at that, the combination of GP6, of GP15, GP16, and then we have the entire link with the tail of the SPP1. And moreover, it has a DNA, and inside of that has a GP18. We have done analysis of a few structures, and then we were trying to understand. But here, possibly within our group, it was a bit too slow, or if you like, might be too lazy. But we were not able to make the structure, and that's exactly the, it has been done by Schroeder and Sophie. They have resolved one of the structures which were interesting. I will show that to you what's going on. But on this level, when we are going to the toy of this long system, that we have a receptor, and it plays quite a role. This receptor is UAB, which was found by Paulo Tavares, and it's mostly sits. It contains the beta sheets and only alpha helices, which is related to in link to the tip, in which provides the signal, which goes up, and that signaling through the, we expect that there is a changes in the structural conformation of these tail proteins, which are opening the valve and of the stopper. It became open, and then the GP18 and the tip, they go away and DNA leaks out. But how we can prove that? That's what we have done that. That's what we analyzed with Yuri Chiban, this system. And in spite of that, one of the elements was not quite well defined. Now I know, and we can improve that. This is so-called, sorry, this is wrong. This is a full, when it goes GP18 and DNA inside, and here it's empty. When after interaction with host receptors, all these things they have leaked out. And then what we can see, we have done the fitting. We know how the proteins interact with each other and what's going on within that. That's what I'm saying. This structure, this part has to be modified according to our new results by X-ray, by cryo-electron microscopy. But the idea in general, that right now, if we will compare what's going on by nature, nature is quite smart. And that's what we are doing, honestly. We are discovering again and again what has been created by nature millions of years ago. And we know how these elements of the structure, they do interact, and the major points, and they're mostly related to the electrostatic issues. We have a different indication of what's going on, how GP6 interact with GP15, and how GP15 interact with GP16. And we know that there is a GP17, we have modeled that, how it goes into the groove of GP16. That is exactly like a whole mechanical system which we are using in our water system. When they connected to each other and how they make each other and how we are can make the different interaction field and not field, and how they just bound to each other. The tail has been analyzed by us at quite a low resolution a while ago, and we have done the low resolution structures about 12 angstrom resolution a while ago for GP17.1 and GP17.1 prime, with which has additional gamma globulin on the top of that, and you can see that. But a group by Schroeder, they have done a high resolution structure compared to us, about 6 angstrom resolution. They have done the fitting, and if you will compare the position and the links, what we are going here to show here is quite significant to that what was done by Schroeder by group of Schroeder, and we can see what's going on and how these beta layers are built, and they're coming from one structure to another. But this is somehow the way that we have to understand how signaling is going on. And that has to be done using a much more complicated system with a nearly full phage with a tip and the receptor. That's exactly what we are having here. It's a general system that we have this huge phage, which is really more as 30 megadaltons, if we will not consider the tail. And we're analyzing with electron microscopy, but we have to combine. It doesn't mean that we don't need NMR or X-ray. X-ray, NMR, they provide us some kind of template. We need to use in bioinformatics and modeling how everything should be developed, and then we understand how the system is working. Okay, that's, I really have to appreciate our teamwork, which we are working together on combining different methodology, different ideas, a lot of skepticism, a lot of encouragement, and how we are doing that. And here are this group which was working on the analysis of images. It's Igor who did the analysis of the connector. Thanos Ignatio, who did the procapsid and capsid. Helen White, she was working quite a lot on the different methods of the analysis of the at low resolution very first structures of the capsid. Celia Plisson was doing quite a lot on the analysis of the tail organization. Yuri Cheban was working right now, was working on the complex of the portal protein with the tail, and now he was helping me quite a lot in sense of the analysis and collecting data. And together with Natasha Lokayano and Dan Clare, they're working on, Natasha was helping me in Berwick College, and Dan Clare and Yuri Chiban were helping to collect me data on this lovely connector, which we have achieved a really lovely resolution. And Sandrine, Mhedi, Isabel, Paula, and Sophie, it's a really very good, nice, friendly team who were working quite a lot and listening. Sometimes are my stupid, sometimes comments, what we can do that, how we can fix that, and what we can improve that. And they had their own ideas how we can implement it, realize in our experiments in EM. Therefore, to have such a team together, it's really very great achievement, and that's why we are able to understand nearly from the head, the top of this bacteriophage, nearly to the end of the tip, how it works and what kind of conformational changes are essential for its activity.
Sorry, Elena.
Shaw and Richard was like, it's a computers, and as I have mentioned, Fred Anderson and really Alex Wagen, they've got very important information for us about the X-ray analysis. And then the data collected were by Michael Sherman, Rudy Lurz, Thorsten Mielke, York, and Celia Plisson, and Natasha Lukayanova. It was really, I was collecting data nearly around the world. Thank you very much for your attention.
Thank you, Anna, for your talk and for a very...
Sorry, I cannot hear you.
Now? Is it better? Can you hear me now? No, for some reason. Thank you for a very invigorating talk. Let's call it this way. And we have time for just one short question, please. Hopefully it will be fixed somehow. If we have technical issues, then we have to thank Yelena for a great talk and continue to the next speaker after a small technical pause. Thank you. Person, can you hear us?
Yes, I can hear you.
Oh, great.
Hello, everyone.
Let me introduce you the next speaker in our section. This is Evgeny Pichkur, and his talk is dedicated to a very vibrant theme of single-ring chaperonins from giant bacteriophages. It's dedicated to their Cryo-EM study. Please begin. You have for 30 minutes.
I believe 15 minutes.
15 minutes? No.
Okay, so okay.
My program says the other thing. Okay.
Okay, so I will talk about cryo-EM structures of single ring chaperonins from bacteriophages, and let me start with a very short introduction to what chaperonins are. So chaperonins are protein complexes that assist the proper folding of synthesized protein in ATP-dependent manner. And there are two large groups of chaperonins. The first one is bacterial ones, for example, Cryo-EM, and the second one is eukaryotic one, for example, TRIC. Now, they both of these groups similar in some way and very different in other ways. So, for example, both chaperonins contain the cavity where the substrate folds, and both uses ATP for its work. But Cryo-EM, for example, requires a cofactor called Cryo-ES for to facilitate protein folding. And Cryo-EM, for example, consists of two rings, and each one of the every single ring is actually homoheptameric. And regarding TRIC, there might be difference, so the subunits are not identical. Now, it is surprising, but there is also another group of chaperonins which are coded in bacteriophages. And I will talk about the structure of the OBP phage of Pseudomonas fluorescens, and on the left there is an image of this phage. So you might appreciate the size of the capsid, about 100 nanometers. And to the right is the negative staining of the chaperonin from this phage. It was predicted by the group led by Lydia Kuruchkina a few years ago, and at the moment it was probably the second known viral coded chaperonin. The first one was from the EL phage, and surprisingly, it was purified as a single ring form. And you can see this preliminary analysis using negative staining, and clearly that this protein is single ring. And this is basically the point where our collaboration started, because obviously you want to do Cryo-EM in this case and to get a reasonable structure. So yeah, speaking of chaperonin itself. So here is a sequence alignment of this GP246 chaperonin compared to group 1 Cryo-EM and group 2 TRIC. As you can see, the ATP binding site is pretty conserved, but there is also a huge difference in inter-subunit contacts. So inter-ring contacts are not conserved in GP246. So this is probably the reason why it was purified in a single form. We have collected a data set of upper form of GP246, and at the moment we were kind of limited by the hardware and the storage, so we collected about 100,000 particles, and we also had to deal with the severe case of preferred orientations. Nevertheless, we managed to get a somewhat reasonable structure, and here is a cross-section of the structure colored by the local resolution. And as you can see, in the intermediate domain, there is a very high degree of symmetry, so C7.5 point group is clearly resolved, but apical domains, which are colored in blue, they're definitely not symmetric. So there is some sort of symmetry mismatch, and we decided to here is the cross sections again of the structure, and it is shown in different angles. The equatorial domain is highly symmetric and also looks a lot like GROEL, but apical domains are quite different. So you can notice that there are actually two different positions of the apical domains. It is color coded on the scheme. So basically, all these there are basically three pairs of domains and one unpaired domain. So it was kind of surprising because we never expected it to be this way. So we have built an atomic model, and it turned out that indeed there are two dramatically different conformations of subunits of the chaperonin. And surprisingly, the first one, the first conformation is very similar to low affinity state of GROEL, is shown in green here. And the second conformation is similar to ATP bound structure of the GROEL. So in GROEL, these conformational changes more or less happens simultaneously. But in this case, in upper form of the protein, there are two different subunits, and it was really surprising at the moment. So I forgot to mention that in GROEL, the intermediate and apical domains are connected by highly conserved residuals, and in our chaperonin OBP, the corresponding residuals are placed by other pole residues, and it seems that it actually has a dramatic effect on the flexibility of the apical domains. Now, the resolution of the structure was about 4.3 angstroms, so not really a great example, not really a good case for building an atomic model. Nevertheless, Pavel decided to do molecular dynamics using Cryo-EM model as restraints for this, and it allowed us to predict the inter-subunit links, so the salt bridges between subunits. They are shown here, then we decided to get structures with the ADP and ATP gamma S, just to be sure that biochemical data is right, and it really depends on ATP for the functioning. And you can see that in this structure, the modeled density for nucleotide is not seen, so it's basically here. Of course, the resolution of this map not enough to clearly resolve it. And surprisingly, we saw that the resolution of the apical domain is even worse than in the upper form. So binding of the nucleotides in some way facilitates the heterogeneity in our sample. And you can see that the apical domains are almost not resolved on both of these structures. So we were puzzled by what exactly happened to our protein, and decided to do three-dimensional variability analysis in CryoSpark. I believe it was done after a week, after the moment the 3D variability became available in CryoSpark. And this is one of the components shown, and you can see that a couple of subunits in A and B form states basically do not move much, but there is a neighbor subunit that clearly changes its state from A to B, and this is basically the reason why we can't resolve anything in nucleotide bound structures, except for equatorial domain, which is symmetric. So here is the illustration of what's going on here. So in upper form, we have 3 pairs of subunits. Both of them looks very similar to different states in Groy's Groyal chaperonin, and we have also 1 unpaired subunit. And when nucleotide bonds to each of these subunit, the heterogeneity rises dramatically, and we can't really resolve anything. Okay, now then we these results were published in the paper in GSB, and then we figured to collect a proper data set with ATP, and you can see that the density for ATP, or perhaps it looks more like ADP, is clearly resolved on this map. So the resolution was about 3.5 angstroms. But again, the apical domain is poorly resolved, and you probably you should keep in mind that the subunit itself is about 60 kilodaltons, so the apical domain is about 1/3 of this number. So it is still a very challenging target, especially for our hardware stuff, including Falcon 2. Now, this is still an ongoing work, and we also figured to collect a small data set with a native substrate for GP246, and we found that we indeed can see some density inside the cavity of the chaperonin. But again, we had to deal with the severe preferred orientation. So you can see that the deletion of some, the removal of some projections helps to some extent, and you can get a reasonable structure without deformation. But again, the effect of preferred orientations is still visible. And here you can see the cross-section, the central slice of the protein, showing the density for the substrate, connecting the apical domain of one subunit and the intermediate domain of the other subunit. Now, another thing we're working on right now is cryo-EM structure of different chaperonin from the different phage. And you can see that compared to the GP246, there is a significant difference, and GP228 looks more like a Groyal, just the single ring of the Groyal. But again, apical domain are very poorly resolved, so we expect the structure to get better when the new software will become available, like flexible refinement in CryoSpark, because again, different approaches like symmetry expand doesn't do much in these cases, and the most interesting part really happens in apical domains and in nucleotide bound states, and when substrate is present. So overall, it is still a very challenging target, and we still expect to get interesting insight into how protein folding happens thanks to the viral chaperonins. Okay, I believe that's it. I would like to thank Olga Skova, who is principal investigator in this work, and of course Lydia Kuruchkina, whose group discovered and predicted the viral chaperonins, and also did a significant part of biochemical work here, and Tatiana Stanichny-Konovalova, who contributed to the scientific part. I believe that she is the main, the first author of this work. And of course, Andrei Mysenko, an electron microscopist in Moscow State, and Yekaterina Maslova, master student. And again, thanks to the Valeria Samigina in Kurchatov Institute and Alexander Vasilyev, also in Kurchatov Institute. Okay, that's it. Thank you very much. Okay, thank you.
Hello, can you hear us?
Hello, yes, I can hear you.
Hello. So I'd like to introduce you to the next speaker. This is Mr. Jan Binovsky with his talk named Baseplate Structure of Bacteriophage Phi812 Reveals Mechanism of Cell Wall Binding and Penetration. Please, you have 15 minutes.
Mm-hmm. Oh, thank you. So good afternoon, everyone. First of all, I would like to thank organizers for an opportunity to present to you one of my PhD projects. But before we go into bacteriophage baseplate structure, let me tell you the motivation behind this project. So Staphylococcus aureus is gram-negative bacterium and common human pathogen causing wide range of diseases from skin infections to pneumonia and sepsis. There have been many strains emerging that are resistant to antibiotics, and even the World Health Organization recognized this as one of the most urgent problems for global health. Yeah. So how can we tackle this problem? Using bacteriophages to treat humans represents an alternative strategy and very convenient strategy in comparison to antibiotics. One of the most potent bacteriophage therapy agents is bacteriophage Phi812. The native virion is composed from the head, native tail, and the base plate. As other members of Myoviridae family, upon host cell attachment, the base plate undergoes substantial reorganization, which leads to tail sheet contraction and subsequent host cell penetration and genome delivery. Using cryo-electron microscopy, we focused on bacteria or on base plates in both states. So I would like to start with the native base plate. The overall shape of the base plate is a compressed sphere with a C3 symmetry. The most prominent features of the base plate are these tripods. The 6 of them are facing up towards the tail, and the other 6 are not very well visible here, but they are here under or from the bottom part of the base plate facing downwards towards the host cell. So let me break down the whole native base plate to its component proteins. And I would like to start with the very center of the base plate. So the central part of the base plate, as you can see here, has been resolved to overall resolution around 3.8 angstroms. Core proteins are the tail spike, hub, and tail tube initiator. Tail spike and hub are trimers, whereas the tail tube initiator is a hexamer. Therefore, the interface between the hub and tail tube initiator mediates the symmetry switch from C3 symmetry of the base plate to the C6 symmetry of the tail. Tail tube initiator together with tail sheath initiator form a base for assembly of the rest of the tail. Then there are also protein modules called wedges. They are formed by 2 copies of GP119 that has a different conformation in this case, and also N-terminal part of the GP120 protein. Going up, we've got the first ring of the tail tube and first ring of the tail sheath. So now let's take a look on the rest of the base plate. Going radially from the base plate to the sides, we've got the arms, 6 of them, composed by 6 copies of adapter protein. Adapter protein, or these arms, serve as a scaffold for binding the tripod complex. Tripod complex is formed by tripod cap protein, which we haven't identified yet, and then tripod base protein, GP122. So these are the 6 tripod complexes that are facing downwards, and there are also there is outer ring of these tripods facing upwards. At the end of the arms, we've got the rest of the wedge protein that connects 2 receptor binding proteins here in red and magenta. So this is the overall structure of the native base plate, but the structure and also protein composition is different in contracted base plate. So now let's take a look on that. Contracted base plate has a C6 symmetry, and we can readily see the difference that this outer ring of tripods is now turned from up going downwards. So that's the turn by more than 180 degrees. The center of the base plate is formed by, well, there is a tail tube in the center of the base plate now in contracted particle, and the rest of the core proteins are tail sheath initiator, 3 proteins forming the wedge that hold the tail sheath. So then we've got adapter protein again, and here very nicely seen the inner ring of the tripod complex proteins, tripod cap and base, and also, as I said before, outer ring of these tripods that are now facing downwards. So this architecture or overall organization of tripods led us to assumption that tripod-based proteins may play a role in host cell binding, and we are now looking into that. We could, on this reconstruction, we could resolve only 1 receptor binding protein, as you can see here. The other one is probably on sites, but it's too flexible to be resolved. So when we compare the native baseplate and contracted baseplate, there is a question, what happens in between these 2 states? And to answer this question, we decided to take a look on the proteins involved in binding and penetration of the host cell. So our collaborators from Madrid, group of Marc van Rij, produced both receptor binding proteins in a recombinant form and solved their structure using X-ray crystallography. So the protein, or the core of the protein, is formed by 3 shaft domains that are well conserved among other different receptor binding proteins and tail fiber proteins from different phages. The C-terminal part of the protein is the domain that probably plays a major role in host cell binding. And also interesting feature of this protein is the insertion domain here, as you can see here. Co-crystallization experiments resulted in 3 putative binding sites per 1 monomer, which makes 9 putative binding sites overall per whole structure. Receptor binding protein 2 has basically the same core structure, except it's missing this insertion domain over here. Here, co-crystallization experiments resulted only in one putative binding site per monomer. So then we take a look on I took a look on the tail spike protein, which is involved in host cell penetration. So the N-terminal part of the protein is embedded in the base plate, and the rest of it sticks out from the base plate. And we could observe it also on micrographs with native particles. So we decided to produce this protein in recombinant form and try to solve its structure using single particle analysis. From micrographs of this recombinant protein, we could readily see that it has elongated shape, it's rather flexible, and so we use single particle analysis to solve this C-terminal external domain. The resolved map, or the reconstructed map, was resolved to overall resolution 3.6 angstroms, and the structure is composed from the central part, that's a squeeze jelly roll, and a very C-terminal domain has a so-called Tim barrel motif or fold. The C-terminal domain here has an enzymatic activity. To be more precise, glycerol phosphodiesterase activity. So we presume that the C-terminal domain is involved in host cell wall degradation. The C-terminal domain has one active site per monomer. So I would like to conclude my presentation by proposing the mechanism of how bacteriophage Phe812 binds and penetrates its host cell. So at the beginning, we've got a native particle that approaches the host cell, and it uses tail spike protein and receptor bindings proteins, and presumably also tripod proteins to scan its environment. Then tail spike protein locally degrades cell wall. Receptor binding proteins can bind to neighboring wall teichoic acids, which makes way for receptor or these tripod complexes facing upwards to turn down and face the host cell wall. All these actions combined trigger tail sheath contraction and host cell penetration. So with this, I would like to thank my supervisor, Pavel Plevka, and the rest of the awesome people in our group. I would like to thank also collaborators, our funding, and core facilities at our institute. You can follow me and or our group on Twitter to stay in touch with our research. Thank you.
Thank you for a great talk. Please, questions. We have time for one short question. No questions. May I ask then the question? You've
Please.
showed the enzymatic activity of the tail spike protein, and this is phosphodiesterase, right?
Yes.
But the first target it meets is peptidoglycan. So we have a different kind of chemical bonding there. It's chemical bonds between the amino acids and other components of peptidoglycan, but nothing with the phosphodiester linkage. How do you explain this?
Well, we haven't tested this experimentally, but all the first chemical or the first structures, I believe that this tail spike protein meets is wall teichoic acid, whether it is teichoic acid or lipoteichoic acid. And so it has been, I researched the literature, and this type of protein motif or the domain should act on teichoic acids instead of peptidoglycan. But there are also other proteins, these core proteins in the base plate, which may also play a role in degradation of peptidoglycan. Some of them have also lysozyme activity or predicted lysozyme activity. So that could be also the reason.
So you can expect the broad spectrum of hydrolytic activity. And if you have the recombinant protein, you can try it against the various substrates then.
Exactly, and that's also another experiment we are looking into. So.
For example, whole cells not able to divide, for example, and you can estimate what are the products of hydrolysis by what is the moieties removed from the surface of a cells by your recombinant protein. Thank you. It's an interesting talk as usual in your lab. Thank you.
Thank you as well.
So we are expecting the next speaker, and we're taking a small technical pause for that. Thank you. Hello, can you hear us?
Hello?
Hello? Yes, can you hear us?
I can hear you. You can hear me?
Fine, yes. I'd like to introduce our next speaker. This is Peter Rosenthal with his work on structural transitions mediating virus entry and membrane fusion, influenza and SARS-CoV-2. Please. You have 30 minutes.
Great. Okay, thank you very much for the invitation to the organizers, and also really thanks to all the speakers, because the science has been really fantastic that I've listened to. So a great event, and look forward to them in the future. As indicated, I'm going to speak on the subject of viral membrane fusion, mostly about influenza, but also about SARS-CoV-2. These are projects that I collaborate with Steve Gamblin and John Scale at my institute. And first I'll be talking about influenza A hemagglutinin changes at low pH. And then I'm going to speak about a related subject on influenza C virus, and then I will relate this to some studies of the SARS-CoV-2 spike protein. I show here a picture of the hemagglutinin trimer ectodomain and also a monomer. For many years, the structural studies of this protein came from X-ray crystallography. It's already been introduced at this meeting by Bridget and Dimitri in their discussions about preferred orientation and tilt. Anyway, so now we're going to explore a little bit more about the function of the molecule. And it has a globular head domain indicated in blue, which contains a receptor binding site and binds carbohydrate receptors containing sialic acid. And then the stalk domain in red is the part of the molecule which is associated with the membrane fusion activities. And so the importance of the protein for the virus life cycle is that it has to attach to the cell surface. It binds, it enters the cell by endocytosis, and at the low pH of the endosome, we encounter the structural changes in the hemagglutinin that mediate the fusion of the viral membrane with the host membrane, releasing the genome into the cytoplasm. And on the left here, I show some slices of tomograms of the virus particle, which shows it densely covered with the hemagglutinin. And at one end here is a patch of the neuraminidase protein, which is a receptor destroying enzyme. And then I have another view of it down the middle, which shows a bit of the internal contents, the dense matrix layer, and then this assembly of ribonucleoprotein particles containing the genome. So really over the talk, I think there's a wide range of cryo-EM techniques that can contribute to an understanding of this process. And, oops. Okay, there we go. It was not moving forward for a second. All's fine now. So the conformational changes at low pH, quite a bit was advanced by crystallographic studies. On the one hand, we have the neutral pH structure, and the structure consists of two disulfide linked subunits, and a cleavage between the subunits activates the membrane fusion activity. So the membrane anchored subunit has a hydrophobic sequence at its very C terminus and a hydrophobic fusion peptide at its N terminus. And then we have the globular domain containing the receptor binding site. So studies by crystallography of fragments of the HA generated at low pH yielded a trimeric molecule like this, of which I'm showing the monomer on the left. And this indicated a dramatic conformational change compared to the neutral pH structure of the membrane-connected subunit, in which there was first an extension at the N terminus, and then additionally, the C terminus of the molecule became co-located with the N terminus. Now, of course, for studies like this by crystallography, this removed the transmembrane and fusion peptides in order to do these studies, but the architecture of the molecules suggests where those segments lie. And so the model for membrane fusion that comes about there is that at low pH, the head domains must become mobile and they can be removed by proteolysis. And then this extension can be thought of as one step, which would extend HA2 probably toward a target membrane and bring the fusion peptide into the target. And then a second motion, which is called a fold back or a jackknife, which brings the C terminus near the N terminus, and that produces this model for membrane fusion, which the extended intermediate then folds back and brings the membranes together. This was all based upon the crystal structures a number of years ago. As way of background to our current experiments, I'm going to show a little bit of the membrane fusion in action by cryomicroscopy, and these are experiments done a number of years ago by Leslie Calder, who mixed virus with liposomes and lowered them to a pH 5, and then after various amounts of time neutralized, and then we could plunge freeze them and look at them in the microscope. So this is imaging directly by cryotomography. And the sorts of things we would see are virions associating with liposomes, the deformation of target liposomes, something first observed in K.K. Lee's laboratory. And we would also find indications of protein bridges between the virus and target liposomes. We could also see the fusion pores, which must be the important goal of the process, as clear space between the virus interior and the target liposomes. So from these experiments, we identified what we thought were the important steps, and these have been performed in a number of other laboratories as well, which includes an initial extended stage where the hemagglutinin is interacting with the target. The target deformation brings the membranes into close contact. And then surrounding these close contacts, we would identify very dense bar features, which were of similar size and shape to the crystal structure fragment at low pH. So this is where we thought the extended intermediate and foldback type intermediates were could be used to interpret these experiments. Now, with with a lot of the progress since then, as we've heard from speakers over a few days now, of the improvements in instruments and also in the programs, rely on CryoSpark, which allows us to classify heterogeneous image data and get high resolution structures where this was not possible before. And these are experiments performed by Donald Benton, in which he took the ectodomain and incubated it for various amounts of time, and after plunge freezing and single particle analysis. And you can see from this very dramatic structure here, you can see the extension of the HA2 structure beyond the tops of the molecule, and a separation or dilation of these head domains. There's the map. Of course, to get higher resolution from various parts of this, we were able to use the techniques of focus refinement. But from this model, which I'm showing here, which is the same one fitting this map, you can see the extension, the heads have come apart, and also there's a part of the HA1 subunit which seems to be grabbing onto the protein just at the point where you would see the jackknife occur. So we think that stabilizes the extended intermediate. And then on the far right is the map of a post-fusion structure, which we see at much lower resolution. So we call this extended state 4, and the reason is because Donald observed between the neutral state, which is state 1, and this extended state, these was able to average additional states where the head domains have slightly come apart with different amounts of dilation. And this first step is one of dilation of the head domains. In the second dilated form, which is further along, there's quite a bit of disordering of the bottom of the molecule, including the release of this fusion peptide. That is, it's not seen there anymore. And then the state 4 contains this extended intermediate, and the fusion peptide in principle is up at the top there, but it is not resolved in these maps, and there are further changes in the helices at the bottom. So perhaps in contrast to the picture I gave at the beginning, this appears to be a really structurally concerted process at low pH, in which the head domains move away, and that head domain movement somehow is communicated to this 30 loop region and to the bottom of the molecule in reaching this intermediate. So those are our current understanding of the flu-A membrane fusion. I wanted to briefly speak about some work we've been doing on the related influenza virus, influenza C, which is unique in containing only a single glycoprotein, not a hemagglutinin and a neuraminidase, but the hemagglutinin esterase fusion factor. So this protein binds a sialic acid receptors, but those that have a 9-O-acetylated sialic acid receptor. And it also contains the enzymatic function that hydrolyzes the receptor and mediates membrane fusion. And as a single glycoprotein on the surface of the virus, you can see it forms these very nice hexagonal lattices here shown in negative stain. That was something characterized also years ago by Hewitt and co-workers. This is the crystal structure, many years old now, of HEF, which you can see is a hemagglutinin-like molecule, but has separate receptor binding sites and enzyme active sites in addition to the parts of the molecule that we think are involved in membrane fusion. And it's possible to find helical arrangements on the surface of the virion, such as those that's shown here. And I have a reconstruction at the right, which shows how trimeric molecules are assembling in that. And we emphasize these studies on these crystalline specimens for many years, thinking that that was going to be the main route to high resolution results. But of course, the progress has meant that one can study it in a more general way. And that is by subtomogram averaging directly on the surface of the virion. And this is work by Steiner Haldorsen, a postdoc in my laboratory. And you can see from these spikes on the surface in these cryotomograms, he was able to resolve this density in side view and top view, and that was about 9 angstrom resolution. And the interesting thing is that it didn't quite match the map of the crystal structure. The crystal structure really needed quite a significant conformational change. That is a splaying of the head domains. And as part of that splaying of the head domains, the central helices also started to zip up together, in some ways solving some of the mysteries of why this crystal structure was different from the flu HA. However, we do think that this this crystal structure is still an important state of the molecule. But in addition, by looking at dimer arrangements, we could see that the splaying of these heads domains was necessary to mediate the contacts in the lattice. So in this picture, I show the HEF molecule, the crystal structure, and then this splayed form we've seen on the surface of the virion. And that splayed form exposes the HEF2 subunit. And by comparison, I show on the right the flu A hemagglutinin extended intermediate from our single particle studies. And so we interpret the state of the glycoprotein on the virus surface as one that's sort of primed for fusion. It's opened up. It looks like a dilated form of the hemagglutinin. So the HEF has this modular construction of a receptor binding site, the hemagglutinin, an enzyme, and then the fusion regions. Fascinatingly, a molecule corresponding to the receptor and enzyme regions of the molecule appears on the surface of beta coronaviruses and in the form of the hemagglutinin esterase, which is a dimer, and I have a structure from the database of bovine coronavirus hemagglutinin esterase. But of course, we know that additionally, the coronaviruses have their spike proteins, which in some cases have, for some viruses, recognize acetylated carbohydrate receptors, as with influenza C. But now, turning to the subject of the SARS-CoV-2 virus, these viruses don't have a hemagglutinin esterase on the surface, and their receptor binding and membrane fusion activities are mediated by this. Now, as Joachim Frank pointed out in his talk, the Cryo-EM has just been fantastic for studies of viruses and viral glycoproteins, and really the amount of work that's come on for SARS-CoV-2 has been inspiring. And of course, I think there are something like 400 spike structures in the database. So what I'm speaking about now is the work of Anthony Robel and Donald Benton in Steve Gamlin's lab at our institute. And here we show the structure of the spike, and on the left I've colored the S1 region in blue and the S2 region in red. And I don't need, having introduced the concept of this globular protein and the fusion-related stalk from the HA, just to point out that similar concepts are involved. Obviously, details may be much different, but also a cleavage via furin, and something that is an important activation for the molecule, in addition to a secondary cleavage site. And the furin cleavage site here is a feature of SARS-CoV-2 and not of the original SARS coronavirus. In these studies, Donald and Anthony mixed the ectodomain of the ACE2 receptor in with the spike ectodomain and resolved all of these many structures in solution. And this includes the native spike protein, including where the receptor binding domain for ACE2 is exposed, and those binding site residues are only accessible in the up position. The receptor binding domains moving their position is something that's made facilitated by furin cleavage. And you can see that they have species where they have 2 ACE2 bounds to 2 receptor binding domains, 3 bound, etc., and also a monomeric form of just the S1, which results from the ACE2 incubation, which is really a disintegration of the spike protein. And I just have one of their movies to show what this looks like, the receptor binding domains going up and several ACE2 molecules binding. And the theme for this presentation is that this binding of the receptor binding domains, they open up and out, and those expose this core of the molecule involved, which is the fusion machinery, and that's the broad idea on how this sort of prime structure comes about. So in summary for the talk, you can see that we applied Cryo-EM to this process. Initially, we were working with virus and liposomes. By cryotomography, we've studied the hemagglutinin by single particle cryo-EM, getting high-resolution structures for the ectodomain. Related studies of the HEF protein on influenza C virus, and then looking at how the receptor for the SARS-CoV-2 is responsible for structural changes, and we think primes the molecule for subsequent membrane fusion steps. Of course, there are many studies of those processes, including structures for the post-fusion molecule, but still a lot to be learned in that area. And having said that, I just wanted to thank members of my laboratory. I mentioned Leslie Calder for her studies of membrane fusion. The work on the HEF molecule was done by Steiner Halderson, and earlier by Kasim Seder, who was there no longer in our labs. Both the much of the work was also supported by the structural biology science technology platform at our institute, led by Phil Walker, and many thanks to Andrea Nans for work on this and many other projects helping us collect data for Cryo-EM, and also to Andrea, Andy, and Phil for work on the computational side. I've mentioned both Donald Benton for his work on the HA, and both Donald and Anthony for their work on the spike protein. And this work, as I said, is collaboration with John Scale and Steve Gamblin. And then lastly, hopefully when everybody's moving around the world, we'll have occasion to meet again. This is where we are in central London. I wanted to thank our funders, which include the Medical Research Council, the Wellcome Trust, and Cancer Research UK, and our university partners, UCL, Imperial, and King's College. Anyway, thanks for your attention.
Thank you very much for this great talk. It's really prominent, and it's covering a tremendous amount of work, of course. So we have a time for questions. Please, your questions. There is nothing in the chat yet. The questions, please. Mm-hmm. So
anyway, not to worry.
I'll give one small question, if possible. Is it known if the action of hemagglutinin moieties is cooperative when they're changing the conformation?
Well, it's been an important question how many hemagglutinins are necessary to mediate membrane fusion. I will say, looking at our experiments where we see the number that can fit around these fusion pores, it looks like a number like 6 or so, but we don't. But I have to say we don't know. But very important question. We do think that the sort of synapses formed between the virus and its target seems to involve an interaction zone of many molecules.
Thank you for the answer. Yes, we have yet to know that, of course, and I'm sure you'll definitely get this.
Well, or someone in the audience may get this.
Thank you again for the great talk. And now we are going for a small coffee break before the next speaker. Thank you. Can you hear us? Great. Let me introduce the next speaker, Dr. Thomas Smith, with a talk on the structural studies of shape-shifting noroviruses. Please. You have 30 minutes. Thank you.
Yeah, thank you. Thank you, everyone, for the invitation and for logging on to see the talk. It would have been much nicer to go to Moscow, to be honest. So the work that I'm going to talk about is we've been working on this virus for a number of years. And I've also done quite a bit of work with rhinoviruses and plant viruses. And in those viruses, we saw conformational changes, we saw structural changes, but in almost all cases, those changes were for the encoding process, for the actual infection process. With this virus, what we're seeing is something quite different. It undergoes a number of conformational changes, and as near as we can tell, it has two functions. One is that it both is evading the immune system, and at the same time, it's also optimizing interactions with the receptor. So it's quite different paradigm than some of the other spherical viruses that we've worked on in the past. So, this is the noroviruses are members of the calicivirus family, and in at least before COVID, it was a fairly serious disease, mostly in the developing world, where in the developed world, usually fatalities are found in young children, but really if you can accommodate the dehydration, it's usually a fine outcome. The interesting thing about it is it's highly transmissible. And so this costs quite a bit of money worldwide, but it only takes as little as 10 particles to cause the infection. So it's incredibly infectious. So back in 1999, Prasad and Rossman, and actually I helped collect data on it, they solved this first structure of a calicivirus, and this is Norwalk virus. Now the genotype designation has been changing this past year, so this is the old genotype designation. There's now 10 different genotypes of the calices. And what you can see is that it actually looks remarkably like Tomaviridae with these protrusions coming up off the surface. And the basic structure is that you have a shell domain, which forms a tight shell around the single-stranded RNA. And then rising off from that, the adjacent subunits in the icosahedron form these P domains or protruding domain dimers. And the P domains are subdivided further into the P1 domain, which is sitting tightly on top of the shell. And then you have the P2 domain, which subsequent studies have showed that that's where the receptor binds, that's where antibodies bind for the most part. So this was what we knew back in 1999. And again, the tight interaction made it look like a Tomaviridae more than anything else. So what we're going to specifically talk about is that in the case of what we're finding using Cryo-EM initially, what we're finding is that the mouse norovirus is quite unlike that initial static picture of the Norwalk virus. First of all, we find that there's this gross flexibility of the entire P domain. So the whole P domain you're going to see moves quite a bit. And then what we've been seeing more and more lately is that there's smaller conformational changes within the P domain, which has a huge effect on both receptor and antibody binding. So in collaboration with Skip Virgin and Cristiano Wobus at WashU, we did the first structure of an infectious virus. This is the mouse norovirus. Now, the great thing about mouse norovirus is that they've developed an infectious clone system, a cell culture system, and an animal model. So unlike the human noroviruses, we can actually make mutations and take it back to the animal to look at form versus function. So the first thing we saw was that actually it looked rather ridiculous. Then that the P domain, rather than nestling down tightly on top of the shell, it's actually rising up off the surface by about 15 angstroms. And it's just lightly tethered by this lympher region. So in the crystal structure, the entire P domain was tightly bound to the shell. But what we're seeing in just phosphate buffer and neutral pH, what we're seeing is it was rising off the shell and just very loosely tethered to the shell itself. These P domains were relatively disordered, whereas the shell, you could easily trace the backbone chain, even at 8 angstroms. So we immediately saw this was something quite different, and it was met with a little bit of disbelief at first. So the most important thing to us was, is this an artifact for some reason, or is it observed in the other genotypes? So we went on and in collaboration with Hansman, we did the structure of a human genotype, this is down here, the human genotype 2. So this is a human norovirus. We also, my lab also did rabbit hemorrhagic disease virus. So that's genotype 4. And then this is the MNV. And it's quite clear that in all cases, we have the P domains are very loosely connected to the shell. And in fact, with rabbit hemorrhagic disease virus, the P domains at the icosahedral twofold axis are almost completely disordered. So it's even amongst the motion, there's in at least RHDV, we're seeing even greater motion depending upon position on the icosahedron. So what we're seeing is that what we saw in PBS, neutral pH, was recapitulated in all the genotypes. And that actually going back to Norwalk, if you look at how they crystallized, it was a very high salt and very low pH. And so then we saw this contracted form. So what we're saying is that under physiological condition, something's going on and the P domains are floating all over the place. So the next thing we wanted to do with Skip's lab was to look at the receptor interaction, because that would be kind of cool. And so initially Skip had identified that CD300LF, it's a small IG-like domain, and what they found was that's the receptor. And so we immediately started making complexes with the virus, and we tried and tried. We just could not see the receptor bound to the intact virus. Well, then after a little while, they came back and said, well, that's not the whole story, in that if you just try to get, like the conditions we were using, you just try to get MNV to bind to its receptor in PBS, they got little to no binding. It was basically background. However, they found through a series of experiments, they found out that actually, though, if you added bile, a number of the bile salts, all of a sudden you now saw significant binding, you saw significant infection. So what they saw was that bile is an almost necessary cofactor to get the receptor to bind. And then this is just showing that actually you can show specific interaction of the bile molecule with the P domain. Okay, so that's great. So it turns out that we couldn't see it bind because it wasn't binding. CD300LF has got a fairly weak binding to begin with. And so without the bile salts, you get negligible binding under the conditions that we were experimenting with. So we said, okay, let's do the receptor complex with MNV, but as a control, let's see make sure that the bile isn't causing any changes in the structure by itself. And quite honestly, we were rather shocked. So this is just recapitulation of all the structures that we had done before. This is just the same prep, the same day, showing that, as we saw before in neutral pH, that in the absence of bile salts, the P domain is floating around and is markedly disordered. You can get it by doing low-pass filtering. You can get an envelope to place the atomic structure of the P domain into the envelope, but it's very disordered, and there's no way you can trace the chain. But the shell itself is easily traced at nominally the 3 angstrom resolution. But the moment you add bile, quite unexpectedly, all of a sudden you get contraction. The entire P domain rotates and falls down onto the surface. And now you can trace the chain quite easily, except for maybe a couple of the residues at the outermost tips in the more flexible region. But just simply adding bile salts, you go from this to this. So again, this contracted form of the virus, that's the form that the receptor actually wants to bind to. And so we were actually quite taken aback. So bile alone gets it into this contracted form. And then just to show you, honestly, how ridiculous this motion is, this is just a morphing between our pseudo-atomic model in the apo form and then the Cryo-EM 3 angstrom structure with bile bound. And you go from, in the apo form, you go from this very flexible, raised above the surface, and then it rotates about 90 degrees and nestles onto the surface of the shell. So this was really, really unexpected. And again, once you get the contraction, it looks very much like the Norwalk virus crystal structure, which is at high salt, low pH. Okay, so then just to show you that the structures that we're seeing are quite believable, we can actually see the bile bound to the core in between the two P domains. So the P domains form dimers So you have 90 dimers across the icosahedral surface, and the cholesterol molecule, the biosalts, bind deep within the recesses between these two P domains. And again, these are the outermost loops. These are where the receptor and the antibodies bind. And down at the bottom, you have the shell. So we've got a good model where we're able to see the interaction between the bile and the P domains. And at the same time, we're working in parallel with Skip's lab and David Fremont. And so they're focusing in on the crystal structure of the receptor. And so this is the receptor CD300LF. This is the structure of the P domain dimer, and then the mauve is in the center, binding between the two P domains. So there's a few loops that we're going to mention again and again. These are the three major loops: A, B, E, F, C, D, and then GH. And what you're going to see is that these loops show a huge amount of motility. And that's going to be in the second part of the talk. But just be aware, these are where the important loops are. So at the same time, we're trying to do a cryo-EM structure of the intact virus with the receptor bound. And again, the CD300LF doesn't bind terribly well, so we weren't able to get very high resolution even in the contracted form. But so using the atomic model from our cryo-EM of the intact virus with just bile bound, and then placing into it the atomic structure of the CD300LF, you get this model. So this is a model built on the atomic structure of the complex along with the cryo-EM structure of our bile complex. And you see that you get very good match in general structure of our actual cryo-EM structure, the receptor bound. And there's no significant conformational change anywhere except you just now have the receptor bound. And so the next question is, is this contraction we see, is it necessary as a part of how is it related to receptor binding? And so one way to look at it, and again, this is purely hypothetical, we're trying to test this through mutagenesis in the in vivo models. But this is just a hypothetical as to one reason why the virus might be undergoing this conformational change, why it might be optimizing receptor binding in the presence of bile. So these little yellow balls are showing the C termini of the CD300LF. So that's where it would go back and attach to the membrane in the intact cell. And you can see that in the contracted form, where the receptor is binding, there's fairly good amount of space, and so we're not getting overcrowding, and you should be able to form connections back to the membrane of the host cell. However, if you take the atomic models that we have and then place it into the expanded form, what happens is that you see this overcrowding of all the receptors. The receptors are all overlapping. So actually, by rotating by 90 degrees, contracting onto the cell surface, you actually have more space for more receptors to bind. Now, is this a thing? Is this really important for receptor binding? We don't know. We're making a series of mutations to affect the rotation, to affect the linker region, to see whether or not it has any in situ or in vivo effects on pathogenesis. So we don't know, but we do know that there is more space for receptors in the rotated contracted form. So they're backing up at this stage. So we see this big change in the entire P domain is flopping around and moving. What are all the possible roles for that kind of flexibility, that ridiculous amount of flexibility in the P domains? Well, so this up here is showing a couple things that we do know. So we know that in the bloodstream under normal serum conditions, we've got a floppy P domain rising way up above the surface. We also know that if you inject the virus into mice, you get antibodies not only to the tip of the P domain, but also to the P1 domain that is normally buried in the contracted form. We also know that you can get antibodies to the shell, again, not exposed in the contracted form. And in human feces, you can see basically a naked shell. So we know that in normal infection, it's not uncommon for the P domains to get cleaved off by proteases. So in contrast, in the contracted form, we think that you might have a boost in stoichiometry, more avidity, and so that you, in the contracted or compressed state, it'll bind better to the cells. So those are possible ideas for why this thing would undergo this ridiculous rotation contraction. But again, the flexibility of the P domain is conserved amongst the noroviruses. Okay, so now the second part is there is a great deal of flexibility in within the P domain itself. So in the initial crystal structure, we immediately saw that these two loops, these A, B, and EF loops, were in two major conformations. So one is we call it the closed form, and the other one is this open form. And so that even in the crystal structure, it's in equilibrium between these two. So we know it's flexible. And then the other piece of evidence that we know that there's flexibility within the P domain is that we generate a series of monoclonal antibodies, and these balls represent escape mutations. So to one class of monoclonals, the escape mutations were on the outermost loops. That makes sense. But interestingly, to the other class of monoclonals, the only escape mutations we found were buried deep inside the P domain. So you get escape, but it's through an allosteric-like process. It's causing some sort of conformational change that blocks antibody binding. So those two pieces of evidence showing that we can see motility in these loops, and we see inferred motility because of the escape mutations. So because the escape mutations were so different, these two different classes of antibodies, we thought, well, they must be binding in very different locales. The short answer is no, they're not. They're actually binding in nearly identical positions on top of the P domain, which, again, we were not expecting this. And we're still working on trying to understand how the escape mutations work, particularly the allosteric ones. So we now have, we did the atomics, the crystal structure of the P domain, we did the crystal structure of the antibody. So now using the Cryo-EM envelope, we can kind of place it in. And again, we have two different conformations of those antigenic loops, this closed conformation and then this open conformation. So again, using the envelope from the Cryo-EM, which is only at about 8 angstrom resolution, we can place the antibody in. And what we saw very clearly is it looks like that the closed conformation cannot bind antibody, that the antibody appears to be binding and recognizing the open conformation only. So we have this very mobile region on the tip of the P domain, and it looks like from our low resolution models, it looks like it's recognizing one and one only. But here's the thing, is that when we did the Cryo-EM structure of the bile salt bound to the virus, we saw conformational change in these loops. So rather than being in the open conformation, it's actually the bile salts bind and close that conformation of the antigenic loop. So this movie will show, it's showing the morphing between the two structures. So this is before bile binds. As bile is binding, the CD loop, the EF loop, and the AD loop all move up towards the surface. And when it does that, it pinches off and buries the epitope that the antibody wants to bind to. So from this, it looked like that bile is pushing the structural equilibrium to the closed form, while the antibody wants to recognize the open form. And again, this is all done with atomic modeling and low resolution envelopes. But the interesting thing is these green spheres here, that's that allosteric escape mutant. So a mutation there blocks the one class of antibodies. So again, so now what we're seeing is antibodies wants to see the open conformation, bile causes the closed conformation, and it's to the closed conformation that the receptor wants to bind. So that was all great. That's a model, but we didn't have high resolution information. So we just recently solved the Cryo-EM structure of just the P domain, isolated P domain with FABs bound. And sure enough, what we see is that the CDR3 loop buries itself deep in between the ABEF loops. So when it splays open, is in the open conformation, that's what the antibody wants to see. Now, from the movie I showed you, it looked like bile is pushing it to the closed conformation. Therefore, bile and antibodies should not be able to bind at the same time. And in fact, that's exactly what we showed. What we see is that as you increase the bile concentration, you have very good neutralization and in the absence of bile. And then as you increase the bile concentration higher and higher, you block all three monoclonals that we have. So it isn't true that when bile binds, it helps receptor, but when bile binds, it blocks antibody binding. So, and again, the only reason why we're able to get this structure was because there's no way we're going to get higher resolution in the Cryo-EM with the intact virus because the P domains are flopping all over the place in the intact virus. So the other question that we're still struggling with was, how does bile binding, how does it cause this rotation and contraction? And it's a little bit difficult to see not in stereo, but the take home is that when bile binds, here's the one subunit, here's the other subunit, that actually what happens is that the two subunits that make up the P domain, they actually rotate relative to each other. And in the apo form, if you try to just align with one of the subunits and try to use the apo structure and place it on top of the shell, it doesn't fit. You get massive collisions between the P domain and the shell. But when bile binds, that rotation actually makes a wonderfully complementary surface between the P domain and the shell. So what we're seeing is that in the apo, you cannot form, because it clashes, you can't form a good interaction between the P domain and the shell. When bile binds, you get rotation, and that forms a complementary surface. Now, again, through mutations, and we need to prove this, but we clearly see a significant rotation of the P domains. We clearly see a complementary surface being formed with bile bonds. Now, again, it doesn't get to the biological reason for this crazy rotation and contraction, but we're still working on that. Okay, so these noroviruses are enteric, so they've got to go through the entire gut. And so we're very much interested in what does it look like in different stages of the gut. And so we simply took the virus and hit it with low pH. So again, same prep, same day, divided it up into two parts. One we resuspended pH 7.5, same buffer, and then the other one we resuspended pH 5 and 7.5. And again, at 7.5, we have a floppy P domain. It's very disordered, but a wonderful shell structure. And then by just simply dropping the pH to 5, it contracts onto the shell, and you can trace the entire chain. So it seemed kind of crazy to me that just simply dropping the pH is somehow mimicking the same conformations that you get when something very different like bile salts are binding. So, yeah, this is a bit complicated, but I'll take you to the key points. So since we're looking at a titration, I wanted to look at particularly the acidic groups. What acidic groups might be getting titrated, dropping into lower pH that could explain the same kind of conformational change that you get at low pH that you get at bile, in the presence of bile. So this is the apo structure. And then you'll notice that crazy linker that's connecting the P domain with the shell, it's actually along its length, it's got a number of acids and bases that are evenly distributed in this expanded structure. However, the interesting thing is this loop over here. So that's that CD loop I was talking about, and his neighboring subunit, the GH loop. And what you'll notice at neutral pH, there are 3 acids, 447, 440, and 443, and that at neutral pH, you'd expect them to all be negatively charged. And in fact, in this structure, the GH loop is pointed straight up, forming an extended beta strands, and they're all pointed away from each other. So they're at neutral pH, they're repulsive, and they move away from each other. What's important though is, and I'm going to show some pictures of that, we always saw them moving, the CD loop is moving around a lot. It turns out that in either the low pH or the bile bound versus the apo, this loop, this GH loop and the CD loop, they want to be in the same position. So if the CD loop moves up, this GH loop can move down. And if the CD loop moves down, this GH loop has to move up. So they're fighting for that same spot. And so I'll show you in the next picture. At low pH, there's 2 massive changes. One is that all of those separated charge residues form a cluster, and some of these are acid-acid interactions, just like we saw in the GH loop. So at low pH, this could be part of the driving force that causes the contraction. But what's interesting is that if you go back to the GH-CD loop, you now have the other conformation. The CD loop is now moved, it's pointing up into the air, right? And actually causes the EF and AD loops to contract and form this closed conformation. And this GH loop spreads out and fills the space that was normally occupied by the CD. So what I've overlaid on this was actually the atomic structure in the presence of magnesium. And you'll see that this GH loop looks exactly the same. So in that structure, they saw magnesium chelating these three acids. So again, we can prove this easily through mutagenesis and structural work, but it looks like if you drop the pH, those three acids can now cluster together because of the titration, protonation of the side chains. Or if you chelate it with a metal, those three residues can now chelate and form interactions. And when you do that, it spreads out this loop and it moves the CD loop up. And so what we're suspicious of is that what's in common with all of the pH and the bile and everything is the movement of the GH and the CD loop control the rotation, control the contraction. So everything begins here. And then just to show you a movie, this is a neutral pH, and then this is just a morph moving, showing that a neutral pH, and then going to acidic pH or a metal bound, it contracts down. So it's this massive movement of the CD loop that we think also controls the rotation and contraction. So again, like we did with the bile, if we're having a closed conformation and the CD loop is moved up, if metals and low pH are doing that, then you'd expect it to block antibody binding, and that's exactly what we see. All three antibodies, if you incubate at low pH, then you block antibody binding. If you add either calcium or magnesium at 100 millimolar or so, you also block antibody binding. So low pH, bile, and metals all seem to cause this conformational change, all block antibody binding. And then I'll take this through really quickly just to show you it's all one big equilibrium. So you have two choices with the P domain. One choice is to go this route to get receptor bound. The other choice is to go this route and you get antibody bound. So in neutral pH and in serum, you have an equilibrium between the open and closed conformation of these two antigenic loops. But in the crystal structure and in the stuff we saw, the CD loop is pointing down. So I think with the CD loop pointing down, you have a very facile equilibrium between these two states. Again, antibody wants to see this, the receptor wants this. So then if you go to the right, you go to step number 3, when bile binds or low pH or metal binds, the CD loop moves up, and then that causes a rotation of the AD, the two subunits within the P domain dimer. That then facilitates the rotation and the contraction onto the surface. But most importantly, it closes this ABEF loop up on top and allows the receptor to bind. And that's step 4. So with it all closed up, the receptor can bind, but antibody cannot bind. It does not recognize this conformation. You don't get competition between the receptor and antibody bond. Now, if you go the other route, if you're going to come down here, in the open conformation, the antibody can bind. And again, it locks it into that conformation, and you have to go all the way back up through the equilibrium to get back to receptor binding. But again, it's in a very floppy, very flexible conformation. And then putting it all together, does this make any sense whatsoever? And so the interesting thing is that in terms of pH, the stomach is obviously very acidic, the duodenum is also very acidic, and so is the colon. Most important, I think, about the acidity is that you're also going to make some of the metals like calcium bicarbonate, you're going to make it calcium chloride, so you can increase solubility of the metals. So the low pH not only is going to induce this conformational change that we see, but it's also going to boost the metal content in the gut. And then this is just showing you metal absorption. The take home is that almost all of the metal absorption occurs at the very end of the small intestine and the ileum. So throughout most of its travels through the gut, it's going to see it's going to see high metal concentration, but also probably even more importantly, you have millimolar, 3 to 30 millimolar of bile salts from the bile duct all the way to the ileum. So again, through most of its travels in the gut, the virus is going to see lots of metal, relatively low pH, but a ton of bile salts. And so in the serum, it's going to be in the floppy, open epitope, open conformation. In the gut, it's being closed up, and it's not going to bind antibody, or at least not as well. And then I thought, Peter just gave the talk a little bit about SARS. The thing that we were excited about is that what we're seeing is that host metabolites, the viruses are using host metabolites to avoid your immune system, to block antibody binding. And then just when we published this, we had some correspondence from Peter's group, and they said, hey, we're seeing the same thing with SARS. So I think that it's a very clever way for the virus to, it's infecting the gut, it wants to be in the gut, and it's going to use all the metabolites in the gut to prevent infection. And in the case of SARS, they're using the metabolite of heme to do very much the same thing. How is that important in terms of vaccine development is that it could occur, I think, well, we're seeing it occur in more than one virus, and that can be taken into account when you're trying to make a vaccine. So clearly what is in the serum in the mice where antibodies are being made, that epitope structure is completely irrelevant to what's actually occurring in the gut at the site of infection. So if you could have a vaccine that better mimic the structure in the gut, theoretically, it would give you a more potent vaccine. And it could explain why it's been notoriously difficult to make vaccines against the human norovirus. It may be that you're not injecting the right antigen. Okay, and then finish it up to thank everybody. This has been a long-term project. Special thanks to Misha. He's been my partner in crime, and he's put up with a lot of bad samples from us. And Skip's lab identified the receptor and the virus for us. Christiana, we've been working with constantly ever since and collaborating. And special thanks to NIH and DARPA and the Seeley Center for support. But also in the 2000s, we were collecting all our data at Bridget's NRAM facility. And then until we got our own Cryos, we were pestering WA quite a bit at the Stanford SLAG for data collection. And that's it.
Mm-hmm. Thank you. Thank you for a great distinguished lecture on a very biological issue covered with structural research. This is a brilliant example of this melting biology and structure together. Now we have time for one short question. We're a bit out of time. Please, questions? There is no questions. Let me check in the chat. Nothing. I have one question. Is it safe to assume that this ability of floppy domain to collapse is some kind of chemosensor of the virus, offering it some required tropism to tissues?
It's a really good question. It's a very good question. We don't know, but I think that usually the norovirus, the infection is considered to be limited to the gut, in the absence of metals, in the absence of bile, it seems unlikely that you're going to get significant infection outside of that.
Mm-hmm.
I mean, you will get some, but in a mouse that has a normal immune system, it's cleared before it causes significant infection.
But pH effect and bile salts effect are the same. I mean, the order of magnitude of the stimulus to collapse the domain.
I'm not sure of the question. I'm sorry.
So bile salt makes the domain collapse, right?
Yes.
And so pH change, lowering the pH, also makes.
Yes.
And they are doing it in an independent fashion.
Right. They're probably synergistic, yes.
Mm-hmm. So probably it's just the freshness seal for the virus, so it does not infect efficiently the tissues where one of the factors is absent, or
That's
both
right.
of them.
More than likely, yes.
Very interesting. So this is a separate chemosensor of the virus particle, offering the additional degree of being sure that the virus is infecting the right tissue.
Exactly. I think so, yes.
Great. Thank you. Thank you. And I'm glad to introduce our next speaker. This is Van Chiu. This is a plenary lecture on a single particle cryo-EM at angstrom resolutions.